Hello students, good morning. This is Sekhar from Msigma, Gokulam. Welcome to this comprehensive coursework live class. In fact, I would like to cover in this morning session, I would like to cover fluid mechanics very quickly, and also I would like to solve the previous year's papers also regarding the comprehensive coursework pertaining to the fluid mechanics, because this subject contains 5 subjects. First I will be taking the fluid mechanics. I will be very quickly covering all the fundamental concepts, so that with these concepts you would be definitely able to answer some important questions given in the examination. So first let me define what may be the questions that may be asked. Let me discuss about that. First is the definition of the fluid. First thing what you need to know is definition of the fluid. How do you distinguish between solid and the fluid? A fluid offers least resistance, very least resistance against shear force. Least resistance against shear force or shear stress. Against shear force or shear stress. Therefore, it keeps on deforming continuously. Therefore, it deforms continuously. It deforms, it's flowing. It deforms continuously or keeps flowing under slightest shear stress. That is how we define the fluid. Okay. All the gases, all vapors, all gases, liquids, vapors, everything is a fluid, because they keep on flowing even under the action of a slightest shear force or shear stress. They can't resist anything. Slight shear force is there, slight shear stress is there. They keep on deforming or continuously keeps flowing there. Then comes to the fluid, important fluid properties. I would like to highlight here. They were asked in the earlier examinations also. Most important fluid is density, you know. Then comes the specific weight, rho g, having the units of Newton per meter cube, standard symbols there. Okay, specific gravity, density of the fluid divided by density of the water. It is a comparative parameter. Specific gravity, which is also called as the relative density, RD or specific gravity, all mean the same. Specific gravity or relative density all mean the same, because the density of the mercury is, because specific gravity of the mercury is 13.6, the density of the mercury will be 13.6 into 1000 kg per meter cube. 1000 is the specific density of water. Standard fluid is water, for which the density is 1000 kg per meter cube. Therefore, its specific gravity is 1. Specific gravity of water is 1. Okay, specific gravity of the density is 13.6. Therefore, it is a unitless quantity. A relative RD or a specific gravity all mean the same, right? So these are the many important properties, and above all, the most likely the question will be definitely coming from this property. If any fluid property is to be asked in the comprehensive exam, this exam, coursework exam, most important liable thing is viscosity. What is viscosity? Viscosity is the property of the fluid by virtue of which there is a resistance offered by one layer of the fluid over its adjacent layer against the relative motion between the layers. As the fluid keeps flowing, there is always a shear resistance, there is a viscous resistance. There is something like a fluid friction. Viscosity you can think of as a fluid friction. Okay. So as the fluid is flowing in any duct or over a body, between the layers, what is the resistance felt by a layer, by the adjacent layer? Because as the layer is flowing, the bottom layer will try to prevent that sliding of that layer. So that resistance is because of the property called viscosity. Okay, I say like coconut oil is a viscous oil, water less viscous oil, air very low viscous oil, low viscous gas, water low viscous fluid. Any coconut oil or a lubricating oils, they are all the high viscous fluids. So it is a property by virtue of which there is a resistance offered by one layer of the fluid over its adjacent layer against the relative motion. So a fluid having more viscosity, they can't flow easily. Therefore, we require to supply more energy to the fluid to maintain the flow if the fluid has got more viscosity. If the fluid has got more viscosity, to maintain its flow, we need to supply more energy to the fluid, because that viscosity of the fluid will offer greater resistance against the fluid, against the flow. Therefore, its energy is liable to drop quickly. So, higher viscous fluids, they require more energy to be supplied to it to maintain the flow. Fine. What is that main important thing regarding the viscosity? Newton's law of viscosity. The very important law in the fluid mechanics, Newton's law of viscosity states that viscous shear stress is directly proportional to the velocity gradient or rate of angular deformation. Other name of it is or rate of angular deformation or rate of angular deformation or rate of shear strain or rate of shear strain, all mean the same. This it has three names there: rate of angular deformation, rate of shear strain or velocity gradient. Mathematically, the shear stress is dou u by dou y. The proportionality constant is the dynamic viscosity of the fluid. Mu is the property, a fluid property which is called dynamic viscosity, which is also called as an absolute viscosity, which is a fluid property, very important fluid property. Lubricating oils will have the very high value of the dynamic viscosity. Its units are, these are the questions would likely be asked. Mu units are Pascal second. Pascal second. Every fluid has viscosity. Some has more, like lubricating oils or the coconut oils, like a starch solution. They all have got the more viscosity. Gases also have got the viscosity, but of very low viscosity. Every fluid has viscosity except the ideal fluid. Only ideal fluid has zero viscosity. There is no such fluid in nature. Only ideal fluid has zero viscosity. All real fluids have more or lesser some viscosity. All real fluids have some viscosity. Gases, they are very low viscous, but they are real because they have the some viscosity, but of very low value. 18 micro Pascal second, that is the viscosity of air. 18 into 10 power minus 6 Pascal second, that is the viscosity of air. And generally the questions may be asked like this: is the viscosity constant for a fluid? No, it will change with the temperature. For liquids, it will decrease with temperature. For gases, it will increase with the temperature. For liquids, viscosity decrease with increase of temperature. Decrease with increase of temperature. For gases, it will increase. For gases, viscosity increase with temperature. Okay. Liquids decrease, gases it will increase. Right. So, fine. Viscosity has got the units of Pascal second. Mu is measured in Newton second per meter square or Pascal second. 1 Pascal is 1 Newton per meter square. Actually, there are two viscosities are there. One is dynamic viscosity and other is kinematic viscosity. There is one more. This is a dynamic viscosity. The kinematic viscosity, it is also called nu. It is defined as dynamic viscosity divided by density, mu by rho. Mu by rho is the kinematic viscosity. Its units are, in SI system only I am mentioning, meter square per second. Meter square per second is the unit for the kinematic viscosity nu. Actually, people been thinking, what is the difference between them actually? See, kinematic viscosity talks about the momentum diffusion rate through the fluid layers, particularly while forming the boundary layers. Kinematic kV of fluid speaks about momentum diffusion rate. That is the reason why momentum diffusion rate through fluid layers. It is something connected with time. Look at the units there. Kinematic viscosity nu talks about momentum diffusion rate through fluid layers. That is why kinematic viscosity is also called as momentum diffusivity. Okay. Kv is also known as the momentum diffusivity. Its units are meter square per second, and we have got the another units for the mu. Mu also has got the unit of poise. Mu is measured in poise, and nu is measured in Stoke. Please remember them. Stoke is the unit of nu. Mu is the unit of poise is the unit of mu. 1 poise is equal to 1/10 of Pascal second. 1 Stoke is equal to 1 centimeter square per second. 1 Stoke is 1 centimeter square per second. 1 poise is 1/10 of Pascal second, or 10 power minus 4 meter square per second. Okay, and this particular Newton's law of viscosity can be plotted on shear stress versus rate of shear strain. It can be plotted on a diagram, this Newton's law of viscosity, and if you have any straight line relation passing through the origin, such fluid is called as Newtonian fluid. All gases, example Newtonian fluids, example air, water, all gases, air, water, kerosene, they can be thought of as a Newtonian fluids, because what is the significance of the Newtonian fluid? For which mu value is constant. If the dynamic viscosity remains constant, it is called as a Newtonian fluid. These are non-Newtonian fluids, maybe like this or maybe like this. This is a dilatant fluid. These are non-Newtonian. This is a pseudoplastic. Pseudoplastic. Generally in the examination they may ask the examples of the what is a dilatant fluid? Shear thickening. It is also called as the shear thickening fluid. This is the shear thinning. Okay. Paint, this example is paint, this is a starch solution. Thick starch solution is an example for the dilatant shear. In fact, for the dilatant fluid, the mu value keeps increasing with the rate of shear strain. Here the mu value keeps decreasing. Actually, I can think of that this mu is the slope, right? The slope is can be thought of slope of this curve. This is can be thought of as mu. X-axis indicates, in fact, this is an elastic solid. Y-axis, x-axis indicates ideal fluid. This is an ideal fluid. Ideal fluid has a zero viscosity. What is the significance of ideal fluid? For which the viscosity becomes 0. Is there any fluid in nature? No. Ideal fluid purely imaginary. Okay, all fluids are real. Okay. So this is this subject is called, this topic is called as a rheology. And if you have any fluid after some initial yield stress, if the shear stress and the rate of shear strain has got a linear relationship, it is called as a Bingham plastic. Bingham plastic, sometimes it is also called as the ideal plastic. Example is toothpaste. Toothpaste is you have to remember this thing. And if anything, it has got a non-linear relationship. This is a thixotropic. example here is printer's ink. Printer's ink. Generally, these are the questions they may ask in the examination. Generally, most of the questions in the regarding the properties of the fluid, they will be focused on the viscosity. Try to learn about the viscosity. What is the dynamic viscosity? What is the kinematic viscosity? What are the units of that? Okay, and what are the Newtonian and non-Newtonian? This is a non-Newtonian. This is a non. What is a Newtonian fluid? Newtonian fluid means mu is constant. You can look at this. A slope is constant. Okay, and if the mu is changing, it is a non-Newtonian. These are all non-Newtonian. Pseudoplastic is a non-Newtonian. Dilatant fluid is a non-Newtonian. But here it is a shear thickening fluid, is a shear thinning fluid. Here the mu is increasing with rate of shear strain. Here mu is decreasing as such. Bingham plastic, after certain initial yield stress, then there is a linear relationship, straight line relationship between shear stress versus rate of shear strain. That is called toothpaste, and this is a non-linear. This is a thixotropic. Example is printer's ink. For the x-axis indicates ideal fluid. For the x-axis, because the mu is 0, that fluid is ideal fluid. For the y-axis, it is an elastic solid. So please try to remember this particular graph, which indicates the Newton's law of viscosity graphically, shear stress versus rate of shear strain, dou u by dou y. This is tau, shear stress. Every fluid has got viscosity. So this is all about the questions may be asked about the viscosity like this. Then comes the very important property called as the surface tension. Sigma. See, the example for the surface tension, you can give many. Supposing there is a liquid water. An insect is able to walk. An insect is able to walk on the muddy water because of the surface tension. You can balance a slight loads gently placed on the surface of the muddy water. If you just place a light weight pin like thing, it can float. It won't sink. Then what is that is balancing the weight of that pin? It is the tension prevailing in the surface. This is air, this is water, say for example. Okay, surface tension is because of what? Surface tension is because of the intermolecular attractive forces called cohesive forces. This is why the surface tension, it is due to intermolecular attractive or cohesive forces. Actually, there are two kinds of forces which we see among the fluid molecules. The intermolecular attractive forces of the same fluid molecules or the liquid molecules among the same liquid. The intermolecular attractive or cohesive bonding, they are called as the cohesive forces. The intermolecular attractive forces between the molecules of the liquid and the molecules of the container, maybe a glass container or whatever it is called as an adhesive forces. Two kinds of forces are there, cohesive and adhesive. Adhesive forces means intermolecular attractive forces between the liquid molecules and the container molecules. Surface tension is entirely due to the intermolecular attractive forces or cohesive forces. It is like this. The interior molecule is being pulled by the same force from all the sides. Therefore, net force on the interior molecule is 0. But if you take the molecule on the surface, this is balanced by this, but there is nothing to be balanced by the downward. So there is a net downward pull on all the surface molecules. All the surface molecules of the liquid are being pulled downwards, pulled inside to maintain the equilibrium. There is a tension developed in the surface of the liquid, which is called as a surface tension. Surface tension, always that phenomenon you will be observing between a liquid gas interface. This is a liquid, this is a gas. At that interface, you will see this phenomenon called surface tension. It is because of the intermolecular attractive forces called cohesive forces. So the tension prevailing in the surface of the liquid is balancing the weight of this pin, the weight of the pin or the weight of the insect that is being balanced by the tension prevailing in the surface of the liquid. and the same surface tension is responsible for the spherical shape of the droplet or the soap bubble. Why the soap bubble is spherical in nature? Why the soap bubble is spherical in nature? Why the liquid water is spherical in nature? Why the cylindrical jet of water is issued from the nozzle is cylindrical in nature? All these shapes are entirely owing to the surface tension phenomenon. Okay, the spherical droplet, water droplet, or soap bubble, or jet of water issued from the nozzle. It is cylindrical in shape. All can be explained by the phenomenon of surface tension. Generally, they will ask very commonly what would be the internal gauge pressure inside that. Because of the surface tension phenomenon which we are seeing here, this is the surface tension, right? Sigma. Because of the surface tension phenomenon, there is a internal pressure, gauge pressure inside the water droplet. The pressure inside the gauge pressure here is more than the outside atmospheric pressure. The pressure inside the spherical droplet or the pressure inside the soap bubble, the pressure inside the cylindrical jet of water, they are more than the outside atmospheric pressure, because of this surface tension. And I am giving the formula. P gauge, these are the things we need to remember. P gauge in water droplet is 2 sigma by R. P gauge in soap bubble, it is 4 sigma by R. P gauge in the jet of water, it is sigma by R. Please remember the formula where R is the radius. P gauge in the jet of water is sigma by R. 2 sigma by R, 4 sigma by R, sigma by R. Please remember the formula. So, most likely being asked is what are the units for the sigma? Sigma is measured in Newton per meter. What are the dimensional formula? ml t power minus 2 divided by this, that is m into t. This is the dimensional formula for the surface tension. Surface tension units are force per unit length. So, what is the definition of the surface tension? Force per unit length. That is the sigma units. So, try to remember the formula and all the units for that. And why surface tension? Okay. Then comes the capillarity. Whenever you are dipping one thin glass tube inside a water will rise. Right? Water is rising. This is called capillary rise. This is the water. If the same glass tube is dipped inside the mercury will dip inside the glass tube as such. See, there is an upper meniscus, there is a lower meniscus actually. So, this is a capillary rise, this is a capillary depression. This is the capillary depression. So, why this phenomenon, capillary rise or the capillary depression? If the surface tension is because of the intermolecular attractive forces called cohesive forces, the surface tension is because of the relative magnitudes of the cohesion and adhesion. Here, in this case, adhesion is greater. See, here the adhesion is greater. Here, adhesion is greater than cohesion. Here the cohesion is greater than the adhesion. Cohesion is greater than the adhesion. That is why this is water is rising here. Here the water is depressing. Actually, there is a so this H is given by the formula 2 sigma cos theta by rho gr or WR. W is the specific weight. Rho gr you can take. And this as you see here, H is for a given liquid, H is directly proportional to 1 by R. That is, the capillary effects will be more predominant. If the diameter of the glass tube what you are taking is relatively small. The capillary effects you can clearly see if the radius of the glass tube is very, very small. That is how the trees can pick up the water from the ground. How do the trees extract the water from the ground? Required for their growth because of the capillary effect, because the roots of the tree are very thin, fine, small diameter passages through which the water can be picked up by the tree and it can be used for its growth. So, the capillary effects you can see in our day-to-day life also. Okay. And theta here is 0 for water here. Here in this case theta is 130. So, that is why this cos 130 is negative, there is a capillary depression. Okay. And then what is balancing? Actually, what is balancing the column? Actually, the column is rising. What is balancing the weight of the column here? Means the component of the surface tension force in the vertical direction. From this only this formula has been arrived. How did you arrive at this formula? The component of the this is theta, this theta you can think. The component of the, like this is the meniscus like this, the component of the surface tension in the vertical direction, the component is balancing the weight of the column. This is the component of surface tension in the vertical direction. Okay, this is theta. Okay. So, the capillary effects are more predominant only when the radius is small. If the r is small, the capillary rise will be more. The capillary effects can be clearly observed or can be clearly seen. Okay. This is all about the capillarity. Then comes the vapor pressure. This is the phenomenon, the pressure exerted by the vapor on the surface of the liquid. This is because any liquid molecule, some of the liquid may vaporize and escape into that space above it, right? The pressure exerted by the pressure exerted by the vapor accumulated on the surface of the liquid under saturated conditions, that can be called as a vapor pressure. This is a pressure that is connected to a phenomenon called cavitation. The question may be asked, what is that fluid property that is linked to the phenomenon called cavitation? It is vapor pressure. Remember, that kind of questions will be asked in this comprehensive. So, which property is linked to what phenomenon? Okay. Surface tension is that phenomenon, that is because of the intermolecular attractive forces that is responsible for maintaining a small loads on the surface of the liquid. Capillarity, that is because of the due to both adhesion and cohesion. If surface tension is entirely due to cohesion, capillarity is due to the relative magnitudes, which is more than the other. So, that is how we can understand the capillarity. Vapor pressure is a thing that is linked to the phenomenon called cavitation. What is cavitation? Very rapid violent pressure variations that may occur during the liquid flow. Cavitation damages the surrounding solid surface, that is because of the vapor pressure. Okay. So, these are the very important properties that you may expect. Actually, the units also are given. For the surface tension is force per unit length, and capillarity is the rise or fall. Okay. So, and another thing is bulk modulus K. We have learnt in strength of materials also, mechanics of materials. It is a volumetric stress by volumetric strain. Bulk modulus is minus delta P by delta V by V. Minus sign only shows that as volume decreases, pressure will be increasing like that. So, this for all the incompressible fluids, for all liquids which are incompressible fluids, K is very high. Which are incompressible fluids, K is very high. For gases, K is low. For gases, K is low. So, these are the properties we know. Its units are megapascal. Okay, then I define a fluid pressure. fluid pressure is normal force exerted per unit area. Any fluid exerts pressure on the boundary with which it is in contact. Okay. What is the force exerted by the fluid molecules as they are striking the solid boundary per unit area is called as the fluid pressure. Fluid pressure is the normal force per unit area. Its units are Newton per meter square or Pascal. One standard atmospheric pressure is 101.3 kilopascal, or 1.013 bar. You can also, bar is the unit of standard atmospheric pressure. If any pressure is more than the atmospheric pressure, it is called as a positive gauge pressure. If this is the atmospheric pressure, if any pressure is more than the atmospheric pressure, it is called as a gauge pressure. And the sum of atmospheric pressure and gauge pressure is called as the absolute pressure. Sometimes if any pressure is less than the atmospheric pressure, it is called negative gauge or vacuum. And then the absolute pressure will be anything if the pressure is given with reference to the atmosphere, by what extent it is more than the atmosphere, that is called positive gauge. By what extent it is less than the atmospheric pressure, it is called negative gauge pressure or vacuum pressure. In such case, the absolute pressure is P atmospheric pressure minus vacuum. Vacuum is the other name of the negative gauge. So, if the P absolute pressure, in this case what is that? P atmosphere plus P gauge. If any pressure is more than the atmosphere, it is called as the positive gauge. In such case, absolute pressure will be atmospheric pressure plus positive gauge. Okay. Try to remember these terms regarding the pressure. Then how to measure the pressure? By using the manometer, U-tube manometer. I will just show you a U-tube manometer. U-tube manometer would have its own manometric liquid, maybe mercury. Mostly that manometric liquid will be mercury. Okay, some air is there, some air or some water is there here. The fluid may be here water. This is water. Okay, we have to just note down the difference in the liquid columns. If this is X and this is U-tube manometer has got some left limb and right limb, right? By noting down this left limb and right limb height difference, we can measure, we can tell what is the gauge pressure at A. The main thing that will be understood while answering the manometer is, here comes the two important laws regarding the pressure. Fluid pressure laws. We have to understand two laws regarding the fluid pressure. Number one, Pascal's law of hydrostatic pressure. Pascal's law. The law states that the pressure at a point is the same along all the directions. In a static mass of fluid, the pressure at a point is same along all the directions. That is called Blaise Pascal's law. The pressure at a point is uniform along all the directions. Px is equal to Py is equal to Pz for a fluid at rest. For a fluid at rest, the law states that for a fluid at rest, the pressure intensity is same. The pressure intensity at a point is same in all directions. This is called Blaise-Pascal's law. Okay. There is one more law here. There is a second thing is in a static mass of fluid, as we go deeper and deeper and deeper, the pressure intensity keeps increasing. Supposing if you take a static mass of the liquid, if this is x, this is y and this is z, all the locations which are at the same depth, they are having the same pressure intensity. At all these locations, the pressure intensity is same. The pressure would not change along all the locations which are at the same depth. The pressure intensity will be the same at all the locations which are at the same depth below the free surface. That is, dou P by dou x is equal to 0, dou P by dou y, that is also equal to 0, dou P by dou z, it is not 0, it is equal to minus rho g, Okay, rho is the density and g is the acceleration due to gravity. That means all these locations are having the same pressure because z is not changing. But here and here, if you just take another location, here the pressure intensity is lesser. That means minus sign shows that, what is the meaning of that minus sign? As we go deeper from the free surface, as we go deeper, the pressure intensity increases. As we go deeper, the pressure intensity increases. Okay, so this is the one important thing we ought to know. And that what are the examples of Pascal's law we can take means, best example is supposing a big weight of a car, it may be car may be having a 1 ton weight, actually maybe more than 1000 kg. That can be lifted by using the relatively small force here. The weight of the car can be lifted by using a very small force. So this is based on the principle of the Pascal's law, which states that the moment you exert a pressure here, that will be transmitted uniformly in all the directions. So this pressure intensity and this pressure intensity is same, but the areas are different. Here the area is different, here the area is different. The area is larger, here the area is lesser, but the pressure intensities here and here are same. That is what is called as the Pascal's law. Pascal's law states that the pressure exerted at a point is transmitted uniformly along all the directions. Okay. The pressure exerted at a point in a static mass of liquid is transmitted uniformly along all the directions. So the location here and here, the pressures are same, but the areas are different. Therefore, this P will be, the applied force P is far lesser than the W. A heavy weight of the car can be lifted by using a relatively small force. So that can be thought of as the best example for the Pascal's law. The hydrostatic law of pressure variation states that as we go deeper and deeper, the pressure intensity keeps increasing. Supposing if we just take for example, if we just take two locations, say here location 1 and here location 2. So definitely P2 will be greater than P1. P2 minus P1 also could be obtained by integrating that equation. P2 minus P1 will be W into, supposing if you take an arbitrary datum here, P2 is more, no? Z1 minus Z2, W into Z1 minus Z2. Z1 is this height, and Z2 is, this is the height. This is the datum, here the Z is equal to 0. Okay. The locations where the depth is more and more, the pressure intensity will be more. And the rate of change of pressure with respect to depth is given by minus rho g or minus W. W is called, what is the W? specific weight of the liquid, that is a product of density and acceleration due to gravity. As we go deeper in a static mass of the liquid, the pressure intensity keeps increasing. At this location, the pressure intensity is maximum because that is the deepest point. Okay, so try to remember this, and coming to this particular manometric equation, same rule can be used here. What is the gauge pressure here? Gauge pressure will be 0. But as you are going deeper, gauge pressure will increase. Supposing if you want to get the PA gauge, I want to get the PA gauge. Here the gauge pressure is 0. Why gauge pressure is 0? Because it is exposed to the atmospheric pressure 0. As we are going deeper, pressure intensity will be increasing. Up to here it has come. What is that? W of the mercury into Y. Here and here the pressure intensity is same. Why? They are at the same elevation. They are at the same elevation. This gives the pressure intensity here. But here and here the pressure intensity is same. Why same? Because they are at the same location and continuous mass of the same liquid. In a continuous mass of the same liquid, pressure intensity is same. Minus, you are going up. Why you are putting the minus? As you are going upward direction, pressure intensity will decrease. That is W of the water into X. So this will give the gauge pressure at A. Gauge pressure can be expressed as a gauge pressure head also. Pressure and pressure head both mean the same, but units are different. If the pressure is mentioned in Pascal or kilopascal, pressure head is defined as a pressure divided by specific weight. What is the difference between pressure and pressure head? Pressure head is nothing but pressure in kilopascal divided by W. W in, what are the units for the W? Kilonewton per meter cube. Specific weight units is kilonewton per meter cube. So this will give the pressure head. Pressure and pressure head both mean the same. The pressure at a location can be expressed as a one column of a liquid, that is called pressure head. Supposing atmospheric pressure is there. One atmospheric pressure is equal to, we know that it is 101.3 kilopascal. But that if you express it as a column of a mercury, that is 76 centimeters of mercury. If the same atmospheric pressure, if you mention as a column of a water, it will be 10.33 meters of water. So the pressure intensity or the pressure of a fluid at a location can be expressed as a column of any liquid. You can express it as a column of a mercury or a column of a water, or column means that liquid column, okay, height. So if the atmospheric pressure is mentioned in the mercury column, 76 centimeters. If the same pressure mentioned in water column, it is 10.33 meters of water, right. So I think you understood the basics of the pressure, and then comes the, that means the main thing what you have to understand is, in a static mass of a fluid, as we go deeper and deeper and deeper and deeper, the pressure keeps on increasing. The rate of change of pressure with the depth will be the specific weight of the liquid. The rate of, for 1 meter depth, by what extent, for if you go from one location to another location, 1 meter deeper, if you go from one location to the another location, if you go down by 1 meter deeper, by what extent the pressure will increase? By it will extend by an extent of specific weight. The rate of change of pressure with the depth will be specific weight of the liquid. That is the last equation, dou P by dou Z is equal to minus W had given, no? W is the specific weight of the liquid, right. Now having understood the fundamental, what is the meaning of pressure, what is the definition of the pressure, and having understood the Pascal, so now I would like to give the hydrostatic forces. Hydrostatic forces on immersed surfaces, on immersed here in this case we have to understand the two words called total pressure and the center of pressure. Supposing you got one horizontal plane, square plane like, which is at a depth of the center of pressure, the centroid of the lamina is at a depth of x bar from the free surface. This is the centroid of the lamina G, which is at a depth of x bar from the free surface. and W is the specific weight, W is the specific weight of the liquid, and G is the center of gravity. And the location of the centroid is at a depth of x bar. Then total pressure, this word you have to understand, the total pressure or hydrostatic thrust, hydrostatic force, hydrostatic thrust on horizontal plane, plane surface, horizontal plane or lamina, it can also be called as a lamina, may be regularly shaped or irregularly shaped, W A x bar, where A is the area of the lamina, W is the specific weight of the liquid, and x bar is the depth of the center of gravity, centroid or center of gravity of the lamina below the free surface. G is the centroid or the center of gravity of the lamina, its depth below the free surface. This is a free surface. Free surface means the surface of the liquid in contact with the atmospheric air. The depth of the center of gravity below the free surface is x bar. Then W A x bar, A is the area of the lamina, will give the total pressure or hydrostatic thrust. Where does it act? It acts exactly at the centroid. This is the total pressure P. The depth of that location where the total pressure is not the pressure, it is the force. Total pressure is the hydrostatic thrust or hydrostatic force exerted by the liquid on a lamina. The total pressure is obtained for the horizontal lamina by using the formula Wx bar. A force is defined only when you know the magnitude, direction, and also the point of application. The point of application of the total pressure on the lamina, horizontal lamina, that which is called the center of pressure. This is center of pressure. Center of pressure. Center of pressure is the point. Where total pressure acts. Total pressure or force. Total pressure or force. Or force acts on lamina. This total pressure is given by Wx bar. And where do they say? For all horizontal laminae, for all horizontal laminae, maybe rectangular or circular, whatever it is, Cp coincides with Cg. These are the questions they may ask. Cp coincides with the center of gravity. Center of gravity and the center of pressure both will coincide for all horizontal laminae. Remember that. For vertical laminae, supposing if there is a vertical laminae, this is a vertical lamina. Here also the formula for the, if this is the centroid of the laminae, if this is x bar, here also the total pressure formula remains same, it won't change. What is that hydrostatic thrust? What is the name of the hydrostatic thrust or hydrostatic force? Hydrostatic force on lamina, it is called total pressure, given by the same formula of Wx bar. For horizontal laminae or vertical laminae, the formula for the total pressure is same. But here the main difference is the center of pressure lies, Cp lies below Cg. This is also called as H bar, depth of the center. What is the center of pressure? It is the location where the hydrostatic thrust acts on the vertical lamina. The formula for the total pressure is same, but the location of the center of pressure lies below the center of gravity. Here H bar is given by x bar plus Ig by Ax bar, where Ig is the area moment of inertia of the lamina about the centroidal axis. Remember this. And inclined plane also, it is the formula is same. Supposing if this is an inclined plane, inclined lamina. supposing if this is the centroid of the lamina, if this is the centroid, here also the total pressure formula is same. W A x bar, W is the specific weight and theta is the angle of the lamina. Here also the center of pressure lies below center of gravity. So this is this total pressure will be acting. This total pressure will be acting like this. This total pressure will be acting. The hydrostatic force will be acting like this. Total pressure symbol is capital P. Total pressure is not the pressure, it is the force. How do you obtain that? How do you obtain the force? By by multiplying the force with the by multiplying with the pressure with the area, we got this hydrostatic force. This is called total pressure. What is the other name of total pressure? Hydrostatic force or hydrostatic force. Okay. For the curved lamina, it will be different. These are all for the horizontal lamina. For the curved lamina, the situation is different. Supposing if this is the curved lamina. For the curved lamina, there are two things will come. If this is the hydrostatic thrust, it has two components, pH and PV. pH and PV are the rectangular components of the two rectangular components of the total pressure P. Here the PV is equal to weight of liquid. These are the questions that may be asked. Weight of liquid contained above curved surface, up to free surface. Weight of the liquid contained above curved surface up to free surface. Supposing this is the curved surface. For example, if this is the curved surface, A, B, C is the curved surface. It has got some weight of the liquid contained above that. There is some liquid there. There is some liquid contained above the curved surface up to free surface, right? Whatever the weight of the liquid contained above the curved surface up to free surface is the PV. pH will be nothing but pH is like this. pH is nothing but if you just take the projection of that curved surface onto the vertical plane, there is a projection. So what is the hydrostatic thrust on that projected area? This is the projection of curved surface on vertical plane, on VP, on vertical plane. If we just take the curved surface of ABC onto the vertical plane, whatever the hydrostatic force onto that projected area, whatever the hydrostatic force on that projected area will be acting as will be equal to the pH. Then P will be equal to square root of pH square plus PV square. So the questions may be asked. If there is a curved surface, what is the PV? What is the component of the total pressure in the vertical direction? That is nothing but the weight of the liquid contained above the curved surface up to free surface. pH will be the what is the projected area? Whatever is the projected area, whatever is the projected area, onto that there is some pH is acting. That there is some hydrostatic force will be acting. This is the pH will be the pH is the horizontal component of P. Horizontal component. You know horizontal component, you know the vertical component. This is a net force, right? Now this is the one important thing. So in the hydrostatic forces, you will be getting the 4 cases: horizontal lamina, vertical lamina, inclined lamina. Lamina means a plane surface. Then comes the fourth one, a curved surface. Okay. For the curved surface, we have to take the total pressure components. One is pH and other is PV. PV is nothing but the weight of the liquid contained above the curved surface up to free surface. pH is nothing but the if you just take the projection of that curved surface onto the vertical plane, there will be a hydrostatic force acting onto that projected area. That hydrostatic force onto that projected area is nothing but pH. Now we know the pH, we know the PV, we can get the P as square root of PA square plus PV square. So we did all the 4 cases of the hydrostatic forces. Then comes the very important thing, buoyancy and flotation. Here comes the very important principle called as the Archimedes principle. What does this principle says? Archimedes principle. Whenever a liquid is, whenever a body is floating inside whenever a body is floating or rather submerged, sometimes it may be submerged. Actually, in case of the buoyancy, we talk about 2 different kinds of bodies. One is called as a floating body, ship, boat, they are all floating, right? Second thing is called as a submerged, submarine, a balloon in air. A balloon in air is a submerged in air. Submarine, going under the water. Warships, submarine, you know, well aware of the submarine. That is a submerged body. A ship is a floating body. Boat is a floating body. So, whenever a body is submerged in a liquid or floating over the surface of a liquid, this body will be displacing some liquid. So, Archimedes principle says that the force of buoyancy which is acting on the body in the upward direction, the body is being buoyed up, being lifted up, is being pushed up by the liquid. The force of buoyancy is equal to the weight of liquid displaced by body. Weight of liquid displaced by body. So, this is called as the Archimedes principle. The principle states that whenever a body is floating in a liquid or submerged in a liquid or submerged in a fluid, because the body displaces some fluid because of its presence, so that weight of that liquid displaced by the body will be acting as a force of buoyancy. Where do that act? Where do the force of buoyancy acts? The force of buoyancy acts at a location called center of buoyancy. Is called center of buoyancy. Already said, any force will be completely defined only when you know the magnitude, you know the direction, and also know the point of application. Direction will be upward. What is the magnitude? Weight of the liquid displaced by the body. What is the point of application? At the center of buoyancy. Where do the center of buoyancy lies? It lies at the centroid of the volume of the liquid displaced by body. It lies at the centroid of the volume of the liquid displaced by the body. What is the volume of the liquid displaced by the body? This is the volume of the liquid displaced by the body. This volume of the liquid has got some centroid there, right? This is. So, at that location center of buoyancy lies, okay. And the principle of flotation, principle of whenever a body is floating in liquid, its weight W should be equal to the force of buoyancy. This is called principle of flotation. The center of gravity may be acting like here. Here the center of gravity, through the center of gravity what will be acting? The weight of the body is acting. And through the center of buoyancy what is acting? Force of buoyancy. The weight of the body and the force of buoyancy must be collinear. They must be equal in magnitude, equal in opposite in direction, they must be collinear. Then only the body will be under static equilibrium. Okay. For a floating body which is under static equilibrium, this weight must be equal to the force of buoyancy. Remember that. This is called principle of flotation. This is called principle of flotation. Because there are only 2 forces acting, they must be equal in magnitude, opposite to direction, and the line of action also should be same, right. And the conditions of equilibrium, if you just look at the conditions of equilibrium, there are two things will come here, conditions of equilibrium. For a floating body, first I discussed for a submerged body. For a submerged body like balloon, a best example is balloon. For a floating body, like ship or boat. For a submerged body like this, there are three things will come. This is a balloon, right? Three kinds of things will come: stable equilibrium, unstable equilibrium, and neutral equilibrium. Stable equilibrium means, supposing if you have the center of gravity here, we have the center of buoyancy here. If you given a slight angular displacement, like this is the center of gravity through which the weight acts. This is the center of buoyancy through which the force of buoyancy acts. Center of buoyancy is the location where the force of buoyancy acts. If the body is given a slight angular displacement due to the wind, the center of gravity position will not change, and the center of buoyancy position also will not change, because same amount of the fluid is displaced. If the body is given a slight angular displacement like this, immediately there will be a restoring couple is developed. Restoring couple, which will try to get back the body to its original position. The restoring couple which gets back the body to its original position. So this kind of an equilibrium is called stable equilibrium. Stable equilibrium. This kind of equilibrium is called as a stable equilibrium. That means if the body is given a slight angular displacement like this, there will be a restoring couple or a balancing. Restoring, which is also called as a balancing couple developed, which will try to get back the body to its initial position. This is called as a stable equilibrium. Condition is, what is the condition is? Condition is G must lie below B. G must lie below B. The location of the G should be, you must have seen in the exhibitions, etc. Small air-filled toys will be there. Like if you hit the toy, immediately it will get back to its original position. You must have seen some one toys will be like that. The toys will be there, and if air-filled toys, if you hit it, immediately it will come back. The reason is there is an additional mass is there. There is an additional mass kept here. There is an additional extra mass. We just squeeze it at the bottom. You will see the additional mass, and that will try to get back the body to its initial position. Because of that, by putting that extra mass, what we are trying to do, you are trying to keep the location of the G below, and B is anyhow at. So G must lie below B. That is condition for the stable equilibrium. Supposing if G lies above B, if you given a slight angular displacement, it won't come back. It will tilt more and more. It will tilt more and more and further. Okay, the body will not be able to come back to its initial position. That is called unstable. This is called stable equilibrium. Unstable equilibrium means the body will move further, and no balancing. There will be a overturning couple will be there. Then G lies above B. If G and B coincide, then neutral equilibrium. The body neither come back nor sink nor overturn. The body will not come back nor overturn. The body will not come back, will not overturn. It stays in the new position. If you given a slight angular displacement, the body assumes new position. It won't come back. It won't overturn. So that because there is no couple developed at all, because G and B coincide, it is called a neutral equilibrium. So remember in the exam, They may ask condition for stable equilibrium, condition for unstable equilibrium, condition for the neutral equilibrium. This is all about the submerged body. Then how about a floating body? A floating body like this. A floating body like this is there, like a ship. This is a floating body, this is all water. Some part is above, right? So for floating body, what is the condition? Here it is not the G and B. It is not the G and B, it is rather the relative positions of M and G, meta-center and center of gravity. Meta-center, here comes the meta-center. So I will explain you about that floating body in this figure. Supposing, what is meta-center? There is a symmetrical shaped body, this is a symmetric axis. This is the center of buoyancy, okay. This is say center of gravity. If the body is given a slight angular displacement rightwards, G will be here only, but the location of the B will shift to the new position because body is displacing more water on its right hand side. The new force of buoyancy it will intersect at one particular central axis. This point is called as the meta-center. Meta-center. This angle, for small angles of heel, the distance between GM is called meta-centric height. So the conditions of equilibrium for a floating body, if M lies above G, implies this is the weight of the body acts, this is the weight, right? This is the center of gravity, this is the center of buoyancy. A floating body is given a slight angular displacement. If M lies above G, stable equilibrium. Remember these conditions. We have to remember for a floating body and for a submerged body separately. For a submerged body, the relative positions of B and G will decide. For a floating body, the relative positions of M and G. If M lies above G, stable equilibrium. If M lies below G, it is unstable equilibrium. Okay. M is called meta-center. What is meta-center? For small angle of heel, the line of intersection of the point of intersection of the line of action of new force of buoyancy, which is acting through B1 with the center line axis of the body. This is called as the meta-center M. Okay. The distance between G and M is called as the meta-centric height as theta tends to 0. For small angles of heel, that is called angle of heel. For small angles of heel, the distance between the center of gravity and the meta-center is called as meta-centric height. For floating body, these are the conditions of equilibrium. So these are the things that may be asked in the fluid statics. Then I'll just quickly do the fluid kinematics. In the kinematics of the fluid flow, we do not bother about the forces that cause the fluid motion. We do not consider the forces that are acting on the fluid. Rather, we will only talk about how the flow is happening. What are the types of flow? What is the velocity? How it changes, acceleration, displacement, time, without bothering about the forces that cause the motion. If you think about the forces, that comes under the fluid dynamics. in the fluid kinematics, there are two kinds of analysis will be there. One is called as a Lagrangian analysis and another thing is a Eulerian analysis. In the Lagrangian analysis, we will be selecting a particular fluid particle as it moves in the flow, we will be following that. We will be just following that particle and how the velocity, acceleration, displacement keep changing with time as it goes in the fluid, as it moves in the fluid flow regime. Like that we do follow various fluid particles. We will not be stationary. The observer himself will be moving along with the particles and I will be observing the changes in velocity, displacement, acceleration, etc. that are occurring for the fluid particle we will be analyzing. That is called as a Lagrangian analysis. On the other hand, observer is stationary. We will select a point in the fluid flow regime and what are the changes with known coordinates and what are the changes that occur in velocity, displacement, pressure, density, etc. we will be observing at that location. And like that we do at various locations. Such observation, such analysis is called as Eulerian analysis. In the Eulerian analysis, we will select a particular location in the fluid flow regime with known space coordinates. We will be assigning some point there P, X, Y, Z and what are the changes in pressure, density, velocity, etc. that occur at that particular location we will analyze. Like that we will do at various locations. The observer will be stationary. We will not be going along with the fluid particles. This is called as the Eulerian analysis. And in the entire fluid mechanics we follow this Eulerian analysis only. Okay. The velocity, first thing what we have to understand is the velocity and its components, right. The velocity of the fluid particle is defined like this. If we consider a streamline is an imaginary line drawn in the fluid flow regime in such a way that the tangent drawn to it at any particular location will indicate the direction of the velocity at that point. So, the velocity of the fluid particle at this location x, y, z is defined like this. If it is undergoing, velocity v is limit ds by dt as dt tends to 0. What is a ds? ds is the displacement of the particle tangential to the streamline at that location p with coordinates p, x, y, z. This v may be having three components u I bar plus v j bar plus w k bar, right. What is that? U, v, w are the x, y, z components of the velocity vector v. Okay. Then u is equal to limit dx by dt as dt tends to 0. V is equal to limit dy by dt as dt tends to 0. What is the dx and dy? Dx and dy are the components of the ds. Dx and dy are the components of the ds parallel to x and y directions. Similarly, w. What is the w? X, y, z direction component along this z direction. This is that is the w component. So, u, v, w are the three mutually perpendicular components of the velocity vector at that location p. Okay. First try to understand this velocity. Then the magnitude of v could be easily obtained as u square plus v square plus w square. Okay, now then having understood the velocity, I will define first of all the types of fluid flow. In the kinematics, we have to understand types of fluid flow. If you thoroughly understand this, you can answer most of the questions in kinematics. First one will be steady and unsteady flows. Steady and unsteady flows. See, what do you mean by steady flow? If various fluid flow characteristics Steady flow means this: if various fluid flow characteristics like velocity, pressure, density, etc. do not change with respect to the time at a particular location in the fluid flow regime, such flows are called as the steady flows. So, if you just take one particular location, the dV by dt at that particular location is 0. This is called steady. Or dP by dt, the pressure also will not change, T is the time, this is a steady. If various fluid flow characteristics at a particular location do not change with respect to time, it is called steady. If the various fluid flow characteristics, if rho, velocity, etc., change with the time at a particular location, in flow regime, it is unsteady flow. Things are changing with time at a particular location, it is called unsteady. But 99% problems we assume as a steady flow. In our fluid mechanics, 99% of the fluid problems we assume it as a steady flow. Uniform and non-uniform flows. Uniform and non-uniform flows. But actually, I forgot to give the example for the steady flow. The flow of a fluid at a constant rate. If mass flow rate is constant, the flow of liquid in a duct at constant rate is steady flow. The flow of liquid at a duct, in a varying area duct or a constant area duct, it can be anything, any duct. If the mass flow rate of the fluid is constant, it is called as a steady flow. In unsteady flow, m dot is not, mass flow rate is not constant. Now what is that m dot? M dot is called as the mass flow rate. Mass flow rate of the liquid in kg per second. If the mass flow rate is constant, it is steady flow. If the mass flow rate is not constant, it is unsteady flow. Now coming to this uniform and non-uniform flows, if at a particular location you are measuring some velocity, same velocity if you are observing at every location. If you are observing the same velocity of the liquid, same pressure of the liquid at every location, that means no variation of pressure or a density or a velocity from location to location at a given instant of time, it is called uniform flow. In uniform flow, if various flow characteristics of fluid don't change from location to location, at a given instant of time, it is uniform flow. On the other hand, that best example is, I am giving the example, flow of liquid in a long constant area duct. In a long constant area duct is steady. In a long constant area duct is steady. flow of liquid in a long constant area duct is is uniform, is uniform. At a varying rate or a constant rate, but it should be constant area duct. Supposing on the other hand, that means steady flow means velocity is not a function of s. S means space or location. On the other hand, if velocity becomes a function of space within the flow region, at different locations you are seeing different velocities, it is called as a non-uniform flow. Implies it is non-uniform. Actually, can you blindly remember like this? What is the meaning of uniform? Same thing everywhere you are seeing. Suppose you enter a school uniform they call. That means you see there, you see here, at every location, if you just look at that at a given instant of time, you are seeing the same uniform, right? That is what is called as uniform. Means what? Same at every place, at every location, at a given instant of time. Things may change with time. Supposing here you are seeing 10 meters per second. At the same instant here it should see 10. After 2 seconds here the velocity may be 15. Here also it should be 15. That is called as a uniform flow. Uniform means no variation of parameters from one location to the another location at a given instant of time. Okay, so you understood that. So I will give the 4 examples here. The m dot is constant. It is steady, non-uniform flow. Definitely it is non-uniform. Why non-uniform flow? Because here the velocity is different to the velocity here, because it is a converging passage. Here the V1 is not equal to V2. It is non-uniform, but the flow is steady. But because if you just take the one location, there the velocity will not change with respect to the time. Here m dot is constant. It is steady, uniform. This is steady and uniform. Okay. And the steady flow, because mass flow rate is constant. Then we have the m dot is not constant but long. That is a long duct, long circular duct. It is unsteady but uniform. M dot is not constant. It is unsteady, non-uniform. I think you have understood the difference between uniform, non-uniform, steady and unsteady. Steady means at a particular location things must not change with respect to time, pressure, velocity or density. Now uniform means at every location you should see the same value, same pressure or same velocity. At a given instant of time it is called uniform. At different locations, see, look at this, here the velocity is different, here it is velocity different, non-uniform but steady, because mass flow rate is constant. Okay. Here mass flow rate is varying, it is unsteady, but it is a converging duct. That means here the velocity will be definitely different at any given time, at any given instant of time. That is why it is unsteady and non-uniform. Right. Now then comes the laminar and turbulent flows. So very important, laminar and turbulent. What is actually really the criteria? Reynolds number. Reynolds number is the criteria to tell whether the flow is laminar or turbulent. What is a laminar flow? If the fluid particles travel in laminae without any intermixing, this is called laminar flow or viscous flow. Laminar, other name of it is viscous flow. Reynolds number, that is formula is Vd rho by mu should be less than 2000 for pipe flow. This is called laminar. Turbulent means there is a continuous intermixing. There is a continuous intermixing of the fluid particles, no order. This is turbulent flow. Here the Reynolds number is greater than 4000 for pipe flow. Laminar and this is turbulent. Okay. Now, then comes the incompressible and compressible flows. Incompressible and compressible. If density of the fluid remains constant or density is not a function of pressure, implies incompressible. Density is not a function of pressure. All liquid flows, example, all liquid flows are incompressible. Any liquid flow by default, if the density of the fluid do not change, if it is remaining constant, this is called incompressible. If density of the fluid becomes a function of pressure, or density is changing, rho is not constant, such flows are called as compressible flows. Example, gases at high velocities, gases at very high velocities, in a duct, that may be a compressible flow. So, important number here comes the Mach number m. If Mach number m, Mach number is velocity of fluid divided by velocity of sound. Velocity of sound in fluid. If m is less than 0.3, incompressible. If m is greater than 0.3, compressible. Remember straightly, it is compressible. If m is less than 0.3, 0.3, incompressible, greater than 0.3, it is compressible. Okay. Then comes irrotational and rotational flows. If fluid particles, while traveling in the flow regime, if it rotates about their mass centers, while translating, this is a translating. The fluid, this is translatory motion. But at the same time, there is a rotation. Rotation of the fluid particle about their mass centers. Such flows are called as rotational flows. If the fluid particles do not rotate, simply translate. Simply translate from, they have only translatory motion, only no rotation. No rotation, it is called as irrotational flow. Irrotational flows are also called as ideal flows. They are also called as ideal fluid flows, potential flows, all mean the same. Actually, why this rotation happens means, the main reason behind this rotation of the fluid particle is viscosity. The rotation of the fluid particle about its mass center while translating in the flow regime is because of the viscous nature of the fluid. Supposing if the fluid has got zero viscosity, if there is no viscosity at all, there will not be any rotation, then the flow would be irrotational. So, inviscid flows are ideal flows, irrotational flows are inviscid flows. Inviscid means fluid having zero viscosity, or ideal flows or potential flows, both mean the same. Why it is called potential? Because there is one function called velocity potential. Thus velocity potential function exists only for the irrotational flows. That is why irrotational flows are also called as potential flows. This velocity potential function phi exists only for the irrotational flows. That is why irrotational flows are also called as potential flows. Okay, just take a small break. Welcome back to the class, dear students. Actually, I have already classified the flows, and there is one more classification called as the one-dimensional, two-dimensional, and three-dimensional flows. If the velocity is only a function of x, it is a one-dimensional flow. If velocity is a function of x comma y, one-dimensional flow means it can be indicated like this. It is a one-dimensional flow. That means velocity is changing only with x. Implies it is 2D flows. It is a velocity is a function of x comma y. If velocity is a function of x, y, z, t, x, y, z, it is a 3D flows. Okay. So we have classified the various flows. Now I will define what is the definition of the streamline. Streamline is an imaginary curve. Streamline is an imaginary curve drawn in the fluid flow regime in such a way that the tangent drawn to it, this is a tangent, right? The tangent drawn to it at any point will indicate the direction of the velocity of the fluid particle at that point. Streamline is an imaginary curve drawn in the fluid flow regime in such a way that if you draw a tangent to the streamline at any particular point, it will indicate the direction of the velocity of the fluid particle at that point. Okay. So this is the streamline. The equation of the streamline also we can easily write it here. The u has got two components. The u x direction component is u and y direction component is v. Therefore, if you just take the tan theta is dy by dx. That is for the streamline, the slope of the streamline, that is v by u, that is v dx minus u dy is equal to 0, or dx by u is equal to dy by v. This is the equation of streamline. Okay. In steady flow, streamlines are fixed in space, whereas in unsteady flow, streamlines keep changing their shape, because in unsteady flows, the velocity keep changing with time. In steady flows, what will happen? Things will not change. Parameters, if they don't change with respect to time, it is called steady flows. Therefore, in steady flows, streamlines are fixed in space. Streamlines are fixed in space. Stream tube is an imaginary tube which is totally bound or surrounded by the various streamlines. These are all the streamlines. Stream tube is an imaginary tube drawn in such a way that it is totally bound or surrounded by the streamlines. So, since there is no velocity component along the perpendicular direction, because streamline earlier, as look at this, streamline, there is no component in this direction, in the perpendicular direction. Therefore, there can't be any flow across the no flow across the stream tube, no flow across the stream tube. Stream tube is an imaginary tube which is totally bound or flow in, flow out. Flow should be along the stream tube only. Okay, no flow across the stream tube. These are all the streamlines. We can say these are all the streamlines. Streamlines completely surround or bound the stream tube. This is the stream tube, right? Path line. What is a path line? Path line is the line traced out by a single fluid particle at successive instants of time. At t is equal to 0 seconds, the velocity is here. At t is equal to 1 second, the velocity is here. At the t is equal to 3 seconds, like this, 2 seconds. So it is indicating the velocities of the fluid particles at successive instants of time. Streamline is indicating the velocities of the various fluid particles at a given instant of time. Look at that. Streamline is indicating the velocities of various fluid particles here, here, here at a given instant of time. Path line is the line traced out by a single fluid particle at successive instants of time. This is the path line. So, if the streamline is indicating the velocities of various fluid particles at a given instant of time, path line is indicating the velocities of a single fluid particle at a successive instants of time. T is equal to 2 seconds, T is equal to 3 seconds, like that. Where the particle is now, after 1 second, after 2 seconds, after 3 seconds, where that fluid particle is there, it is called as a path line. Then streak line. Streak line, supposing one dye is added. So there is one point I have considered. So to that fluid particle, there is a, so this is a T is equal to 0 seconds, one fluid particle is ejected, is traveling like this. At T is equal to 1 second, T is equal to 0 second, whatever the passed to this point, that is a trajectory here. At T is equal to 1 second, this is the dye is added. So streak line is the line traced out by a various fluid particles passing through a fixed point. It is the line traced out by various fluid particles passing through a fixed point. Supposing whatever the particle that is passing through the T is equal to 0 seconds in the past, somewhere here. In the past, T is equal to 1 second, T is equal to 1 second, it is like this. So at this moment, T is here. At this moment, T is at 1 second, and this T is equal to second. At this moment, this particle may be here. Okay. At this moment, at T is equal to 3 seconds, whatever this is a particle is here only. So if you join all these, what you get, the streak line. This is a streak line. Okay. So various fluid particles are passing through a fixed point. Now at this moment, at this instant, the fluid particle which has passed through this point at 0 second is here. At T is equal to 1 second in the past, whatever is passed at this moment, it is here. At the T is equal to 2 seconds in the past, it has passed here, it is now here. So like this, like T is equal to 4 seconds. If you join all these, what you get is a streak line. Okay. For steady flow, this is the question being asked. Streamlines, path lines and streak lines are identical. Streamlines, path lines and streak lines all are identical. All are identical. Whereas unsteady flow, they are different. In unsteady flow, they are different. I hope you understood there. One dye is being added here. So that is that now at this moment, 0 second, the fluid particle which was passed some time ago at 0 seconds, now it is here. Some time ago, whatever after 1 second, some more particle may be passing, now it is here. So if you join all these, what you get is a streak line. acceleration limit delta V by delta T as delta T tends to 0, right. This A is equal to AX I bar plus AY J bar plus AZ K bar. Okay. This AX, these are the acceleration components along the x direction, y direction, z direction. AX could be written as U into dou U by dou x plus V into dou U by dou y plus W into dou U by dou z. This is called as the convective acceleration along x. This is dou U by dou t. This is called local acceleration along x. This is called convective acceleration of fluid along x. Local acceleration of fluid along x. U into dou V by dou x, dou V by dou y, dou V by dou z plus dou V by dou t. This is the convective acceleration along x, along y, along y. This is the local acceleration along y. See, what is this convective acceleration? The change in velocity, convective acceleration along any x direction is the change in the velocity component along that direction from location to location. This is called convective. What is the local acceleration along x? Yeah, the velocity has got one component along the x direction, that is u. Its change with respect to time at a particular location, that is called as a local acceleration. In uniform flow, similarly we can mention for the z direction also. In the same lines you can write for the z, but only thing is now you have here the w. Okay. In uniform flow, convective acceleration along any direction is 0, whereas in steady flow local acceleration along any direction is 0. In uniform flow, convective acceleration along any direction is 0, whereas in steady flow, local acceleration along any direction is 0. Okay. Now I define two important scalar functions, velocity potential and stream function. What are velocity potential phi? Phi is a scalar function of space and time. It is a scalar function of space and time. Scalar function of space and time defined in such a way that whose negative derivative with respect to any direction is the velocity component along that direction. Whose negative component along the y direction this is the stream function phi. It is a scalar function of space and time defined in such a way that whose negative derivative with respect to any direction will give the velocity component of the fluid along that direction. Okay. This phi exists only for the irrotational flow. Exists only for irrotational flow. That is why these irrotational flows are also called as potential flows. Okay. Now the slope of equipotential line. What do you mean by equipotential line? If the value of phi is same, suppose if you draw a line, the value of phi is same at every point on that curve on the xy plane, that line can be called as a equipotential line. Equipotential line is the line on which the value of phi, if you calculate at every point on that curve, on that line, it will be the same. The slope of equipotential line on xy plane, equipotential line, that will become dy by dx for constant phi is equal to minus dou phi by dou x divided by dou phi by dou. What is minus dou phi by dou x? Minus u by minus u by v it becomes. And if any function phi that satisfies Laplace equation that is dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to 0, Laplace equation, or del square phi is equal to 0, will indicate some irrotational flow. So if you want to prove a given flow as irrotational, check that whether Laplace equation in phi is satisfied or not. Okay. Now if I define one more function called as a stream function psi, but it is defined usually for the two-dimensional flows. If the phi is defined for x, y, z in t, this is defined only for the two-dimensional flow. Psi is a function of space and time defined in such a way that whose derivative with respect to any direction will give the component of the velocity component in the perpendicular direction. If this is x, this is y, if you take the derivative with respect to x, you will get the v. If you take the derivative with respect to y, you get a anti-clockwise sense. You have to look that. Okay. So this is called as a stream function. And the stream function, if you just look at this slope of the stream function, dy by dx for the constant psi, it will get minus dou psi by dou x divided by dou psi by dou y. It becomes v by u. This is the slope of streamline. It is nothing but the slope of streamline. That means for the streamline, the value of psi is same at every location. If you just look at the streamline, the value of the psi, stream function psi, is same along all the locations. Okay. Now if you just take the product of dy by dx constant phi into dy by dx for constant psi, this is a psi, no? It will be minus u by v into v by u. It becomes minus 1. That means the product of these slopes are becoming minus 1. That means they must be perpendicular. Constant stream function line, that is equipotential line, and the streamline, because stream from constant along the streamline, the value of psi is same at every location. That means equipotential lines are orthogonal to the constant stream function lines. That is a very important point. That is, equipotential lines are orthogonal to constant stream function lines, are orthogonal to constant. This is if this is a streamline, this is a streamlines. These are the equipotential lines. They are the they cut orthogonally. Just look at this. They cut orthogonally at every location, orthogonal to. In flow net, such thing is called as flow net. Such grid is called as flow net. They cut at 90 degrees to each other. Okay. So this is a very important point. So we have mentioned, and there will be 3 rotation components will be there. Flow is irrotational if 3 rotation components omega x, omega y, omega z are 0. These are what are all the rotation components of fluid about x, y and z axis, about x, y and z axis. They are called omega x, omega y, omega z 0. The flow is irrotational. Then I'll just write the what is omega x there, half into omega z dou v by dou x minus dou u by dou y. So many its units are radians per second. I just written the rotation component about the z axis. For the 2-dimensional flows, it is just sufficient to prove the 2-dimensional flow in x and y. It is just to prove the omega z is equal to 0. If it is 0 means the 2-dimensional flow is irrotational. If the flow is irrotational, all the 3 rotation components will be 0. If it is a 2-dimensional flow in xy plane, it is just sufficient to prove the omega z is equal to 0. If omega z is equal to 0, the 2-dimensional flow in xy plane is irrotational. We don't have to check all the things. Okay. So these are generally in the kinematics of fluid flows, what may be asked is, they may ask about the stream function, velocity potential. They may ask about what is a streamline, path line, streak line, and rotational, irrotational, laminar, turbulent. These are the main things that may ask in the kinematics. Now going to the dynamics of fluid flow. This is a very important because here we deal with 3 conservation rules: conservation of mass, or continuity equation, conservation of momentum, or impulse momentum equation, conservation of momentum or impulse momentum equation, anything is okay. Newton's second law of motion. It is a basic form of modified form of the Newton's second law of motion. It is Newton's second law of motion only. Then comes the conservation of energy. Okay. First, I'll write the differential form and differential form of this. In fact, in the conservation of momentum, we may have the 2 things there. That is Euler's equation of motion, and Navier-Stokes. Navier-Stokes, both are conservation of momentum only. Then this is the most important equation, which is called as Bernoulli's equation, law of conservation of energy. This is Bernoulli's equation. Conservation of momentum is either Euler's equation of motion or Navier-Stokes equation of motion. There are two different equations are there. Conservation of mass. This m dot is constant, mass flow rate is constant. This is the velocity v1, this is the velocity v2, this is the area a1, this is the area a2. Okay. For in steady flow, that is a condition. In steady flow, what do you mean by steady flow? Various flow characteristics at a particular point will not change with respect to the time. Okay. In steady flow, m dot is constant, that is rho 1 a1 v1 is rho 2 a2 v2. But for incompressible flow, if flow is incompressible, rho is constant. If the flow is incompressible, rho 1 is equal to rho 2. A1 v1 is equal to A2 v2. That is, discharge is constant. That is, discharge Q is constant. This is in the finite form. In differential form, same conservation of mass in differential form for steady flow, for steady incompressible flow, dou u by dou x plus dou v by dou v by dou y plus dou w by dou z is equal to 0. This is divergent v, del v is equal to 0. This is the differential form of in the differential form continuity equation. This is the, in the differential form continuity equation. Remember, conservation of mass for three-dimensional, for steady three-dimensional flow, incompressible three-dimensional flow, del v is equal to 0. This is the differential form, this is in the finite form. Okay. Then if you write the conservation of momentum, Newton's second law of motion, conservation of momentum. Generally, when you talk about the fluid element, whenever a fluid element is undergoing a motion, there may be a varieties of forces we may be acting, causing the fluid element. A fluid element is undergoing a motion. What are the most important forces we need to consider to write the Newton's second law of motion? Conservation of momentum is another form of the Newton's second law, right? Newton's second law of motion, F is equal to ma. And Newton's second law always deals with a force. So, what are the forces we need to consider while writing the impulse momentum equation or conservation of momentum? What are the forces that are acting over a fluid element? Main force is gravity, weight of the element, mg. Second thing is the pressure force, most important. Second thing is the pressure force, which always act normal to the area. Third thing is the viscous force. The main important are these three: gravity force, pressure force and viscous force. Okay. Other forces, there may be some other forces like surface tension force, compressibility force, turbulent forces may be there, but they are insignificant. The main important in order of priority are gravity force, pressure force and viscous force. This gravity means mg, pressure force always act normal to the area, always normal to the area. Viscous force always acts along the area. These are the viscous force. This is the element. This is the gravity, no? Gravity always acts as mg, right? So, gravity, pressure or viscous, these are the main forces we need to consider in the Newton's while writing the impulse momentum equation. Then we have to write the net algebraic sum of all the forces acting on the element along the x direction should be equal to the mass times acceleration of the element along the same direction. So, then if you write this Fgx plus Fpx plus Fvx, if it is right, the rate of change of what is the Newton's second law of motion says? Newton's second law of motion, net algebraic sum of all the forces, net algebraic sum of all forces acting on element along x should be equal to the rate of change of its linear momentum along x direction. The rate of change of its linear momentum along. This is called as this equation is called as the Navier-Stokes equation of motion. In the Navier-Stokes equation of motion, we consider, I will write for the sample sake, x minus 1 by rho into dou p by dou x is equal to u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z of course. This is the plus mu into dou square u by dou y square. And that means you are talking about it talks about viscosity, this talks about this is the body force potential. So, this is the body force potential. This is the talking about pressure force. This is the for steady flow. This is for the steady flow. This is again the last one is the viscous forces there. Particularly for the boundary layer, these are very important equations that we need to write. And if you write the Euler's equation of motion, which is also a conservation of linear momentum, Euler's equation of motion, which is also conservation of linear momentum, it considers only two forces, that is sigma Fx is equal to max, which we consider only gravity and pressure. It considers only gravity and pressure. Only gravity and pressures are considered. This will be in the further streamline. It could be written as dp by rho plus vdv plus gdz is equal to 0. See, Euler's equation of motion is a first order equation. Navier-Stokes equation of motion is a second order equation. We have to notice that Navier-Stokes equation of motion is a second order equation. Euler's equation of motion is a first order differential equation. When you integrate, this is for along a streamline, this is the or we could write in another way also, x minus 1 by rho into dou p by dou x is equal to ax, that is u into dou u by, for two dimensional flows. For the two dimensional flows, we can, viscosity is 0. Euler's equation of motion, the main assumption of Euler's equation is fluid is, main assumptions are fluid is inviscid, flow is steady flow, and fluid is inviscid flow. Flow is inviscid, no viscous. Viscous forces are not considered in the Euler's equation of motion. The main difference between the Navier-Stokes and the Euler's equation is, in the Navier-Stokes we consider the pressure, gravity and viscous. In the Euler's equation of motion we consider only pressure force and gravity force. No viscous mentioned there. In the previous one, you see, we have the viscosity here showing this. Now, by integrating this Euler's equation of motion, we get the most important equation called Bernoulli's equation, P by W plus V square by 2Z plus Z is equal to constant. For a fluid flow, for this is also valid only for the steady inviscid flows, no viscosity, inviscid flows. Here P by W is called as pressure head, V square by 2G is called as velocity head, and Z is called as potential head or datum head. Potential head or datum head. All are in meters. So the Bernoulli's equation says that the total head of a flowing fluid between any two locations remains the same. So what is head? Head means energy per unit weight. Head means energy of the flowing fluid, per unit weight. Energy of the flowing fluid per unit weight is called as the head of the fluid, measured in meters. Okay. So it is a law of conservation of energy. But this is only called as Bernoulli's equation. This is famously known as Bernoulli's theorem, Bernoulli's equation or Bernoulli's theorem, which comprises three things: pressure energy, kinetic energy and potential energy. Pressure energy per unit weight, kinetic energy per unit weight and potential energy. So Bernoulli's theorem states that, what is Bernoulli's theorem? Bernoulli's theorem states that the total head of flowing fluid remains constant between any two points in the fluid flow, if there is no loss of head, P1 by W plus V1 square by 2Z plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. This is called as the Bernoulli's theorem, very most famous theorem in fluid mechanics, which is also law of conservation of energy. This is the Bernoulli's theorem is the law of conservation of energy. Euler's equation of motion is the law of conservation of momentum. Navier-Stokes equation of motion is the law of conservation of momentum. But only thing is Navier-Stokes equation takes one force extra, that is viscous. Continuity equation is a law of conservation of mass. Okay, remember this. And this particular theorem could be used to measure the discharge also in the venturimeter. So in the venturimeter, what do? You measure the connect a U-tube manometer between the inlet and the throat section, and you will calculate the discharge. Inlet and throat, this is the throat section, this is the inlet section. You will just see, as the area is decreasing, velocity is increasing. That means, as the area is increasing, velocity is increasing. Z is same elevation, same height, therefore pressure must be decreasing. By measuring the pressure difference between inlet and throat, by measuring the pressure difference between inlet throat by using the U-tube manometer, we will be measuring the discharge. A1, A2 root 2 GH by, this is the square root of A1 square minus A2 square into coefficient of discharge. CD, this coefficient of discharge is this actual discharge. Coefficient of discharge is the ratio between actual discharge and theoretical discharge. Its value will be somewhere around 0.97 or 0.98. So Bernoulli, this instrument is called as the venturimeter. What for the venturimeter is used? To measure the discharge. This is the actual discharge of liquid. Okay, it can be used to measure the flow rate or the discharge of any liquid flowing through a pipe. Venturimeter is a converging diverging passage. Diverging passage will be very long. To avoid the flow separation, this diverging portion will be very long. This angle will be, should not kept, this theta should be less than 8 degrees. Okay, 8 degrees. Then only that to avoid the flow separation, etc. actually. So from here to here pressure will decrease, from here to here pressure will increase. So the diverging portion will be long in length as compared to the converging section. This section is called as a throat. A U-tube manometer is connected. This difference is noted, this difference in mercury levels, manometric liquid levels. This is SM. If the flowing liquid has got specific gravity X, this H could be obtained as Sm by S minus 1. Okay. So this is the principle. Venturimeter is meant for measuring discharge. Similarly, we have the petard tube also. Petard tube is also meant for measuring the velocity. Just by putting for measuring the velocity, just by noting down that level of liquid rising. This is a petard tube to measure the velocity. V is equal to Cv into root 2 GH. So this instrument is called as petard tube to measure the velocity V. A L-shaped tube where a narrow tip will be there, narrow tip opening will be there. Narrow tip opening will be there. This point is called as the stagnation point, because the liquid will become stagnant there. The liquid will become stagnant once it enters that narrow hole there, and that velocity head will be converted into the pressure head. So you can measure the velocity of the flowing liquid. This instrument is called petard tube. Similarly, you have an orifice. In the similar lines, orifice tube will be there. The orifice tube also measures discharge. Petard tube measures velocity. For velocity, this is for measurement of velocity. Orifice tube measures discharge, but it is not that accurate as that of the venturimeter. Venturimeter is more accurate as compared to the orifice meter. Okay. So actually, for if there is a loss of head is there, supposing there is a pipe, if there is a loss of head is there between 1 and 2, you can write the Bernoulli's equation like this. Total head at 1, total head means sum of pressure head, velocity head and datum head, because any flowing fluid will contain three forms of the energies: pressure energy, kinetic energy and potential energy. Okay, total head at 1 minus loss of head. Why there is a loss of head? If the flow is happening like this, why there is a loss of head? Because of the viscosity, because of the main is because of the fluid friction. The loss of head is due to the fluid friction. Should be equal to the total head at 2 for writing the Bernoulli equation. Okay, supposing if you want to calculate this loss of head, how to calculate the loss of head due to friction? How to calculate loss of head due to friction is HF. How to calculate means, again there are two different, this loss of head due to friction is mainly, the head loss is mainly because of the frictional head loss. That there are some other losses, entry loss, exit loss, loss due to converging loss due to divergence, loss due to convergence, many other loss is there, but major head loss is because of the fluid friction. What will cause this fluid friction means viscosity itself. Viscosity itself will cause, and the pipe roughness also may cause the this loss of head. So for calculating the loss of head, we have a different equations there. We have the, for laminar flow, we have the Huygens-Poiseuille equation. For laminar flow, and for turbulent flow we have the Darcy-Weisbach equation. First for laminar flow I write. For when you say laminar flow, the fluid particles must be travelling in laminae without any intermingling. What is the criteria? Your Reynolds number should be less than 2000. The fluid particles are travelling like this. Reynolds number should be less than 2000. What is the formula? What is the definition of the Reynolds number? Inertia force by viscous force. This is the formula. This is the definition of the Reynolds number. Reynolds number is defined as the inertia force by viscous force. Its formula is Vd rho by mu. So for the laminar flow, where the velocity distribution is a parabolic, right? Axis symmetric parabolic. What is this velocity distribution? It is parabolic. If this is the u, if this is the r, u is a function of r. What kind of function? It is a parabolic velocity distribution. Parabolic velocity variation. Here the velocity is 0 for the fluid particle because one layer attaches. Because of the viscosity, one layer attaches itself. Here the velocity is 0. You have the maximum velocity at the axis. 0 velocity at the pipe boundary. Okay. With the 0 velocity at pipe boundary and the maximum velocity at the pipe axis. And maximum velocity, we have the maximum velocity as the fluid particles travel through a pipe at a given cross section. If you just look at the given cross section, at a given cross section, this is the cross section. You have the 0 velocity of the fluid at a given cross section of the pipe. We have seen the 0 velocity at the pipe boundary with maximum and Vmax at the axis. And Vmax at the axis. This is the, I am talking about the laminar flow as long as the Reynolds number is less than 2000. For the pipe flows I am talking. Okay. And this velocity distribution is given by like this. This is the velocity distribution. This is x direction. This is r. So what is this minus sign shows? And in the direction of the x, pressure keeps decreasing. So r is the radius. Small r is the radius at any radius measured from the axis. If you take r is equal to capital R, look at this, when you take r is equal to capital R, this velocity is 0. This minus sign only shows that as x is increasing, pressure is decreasing. Minus 1 by 4 mu into dou p by dou x minus r square into r square. Parabolic velocity distribution. Okay. And incidentally, this V max will be exactly twice the average velocity. Average velocity given by discharge divided by area, average velocity. Okay. This is so, and this if you just take the shear stress distribution, it will be in the same laminar flow, shear stress variation. If you see shear stress variation, shear stress varies linearly with respect to the radius. This is r, this is x. This is the shear stress varies linearly. Tau is equal to r by 2. Tau is the shear stress at any radius. At any radius r measured from the axis. We have the maximum shear stress at the pi boundary. Tau maximum shear stress will be at axis. At axis, that means shear stress varies linearly with respect to r. Shear stress varies linearly with respect to r. In laminar flow, all this is for the laminar flow only, as long as the Reynolds number is less than 2000. Maximum shear stress at the pi boundary and zero shear stress at axis. This minus rho p by dou x is the pressure gradient. This is called as the pressure gradient. Pressure gradient in the direction of flow, which is a constant. Which is a constant. Pressure gradient, this is in the direction of flow. X is the direction of flow. So if you just look at the earlier equation, velocity varies parabolic. Velocity varies parabolically. This is axisymmetric parabola. Axisymmetric parabola. And shear stress varies linearly. This is very important. Try to remember these points. Shear stress varies linearly, velocity varies parabolically. Parabolic velocity distribution. This is axisymmetric parabola, right? So this how to calculate what is the Huygens-Poiseuille equation? I am giving the Huygens-Poiseuille equation for calculating head loss due to friction. HF is equal to 32 mu VL by WD square. Where what is that HF? Head loss due to friction. This is that is also called as P1 minus P2 by W, where L is the length, V is the, V average velocity, discharge divided by cross-sectional area. This is the Hagen-Poiseuille equation exclusively for laminar flow. Exclusively for laminar flow only, the Hagen-Poiseuille equation valid only for the laminar flow. W is the specific weight, W is rho g, we know that, the specific weight, where L is the length of the pipe between two sections, pressure drop. No? For turbulent flow, through pipes, where Reynolds number is greater than 4000, we have the head loss due to friction calculated from very famous equation known as FL V square by 2GD. It is also called as Darcy-Weisbach equation. Where F is called Darcy's friction factor. Actually, though this is derived, Darcy-Weisbach equation is derived from the turbulent flow. Darcy-Weisbach equation we can write for laminar flow also. That is why in laminar flow F is equal to 64 by RE. Remember this equation, where RE is the Reynolds number, Vd rho by mu. In laminar flow, friction factor, what is that? F is called Darcy's friction factor. F is called Darcy's friction factor. But in turbulent flow, friction factor is a function of not only Reynolds number but also due to the relative roughness of pipe. Roughness of the pipe also will decide relative roughness. Pipe roughness also will decide friction factor. F is called Darcy's friction factor. Remember, F is called Darcy's friction factor. In laminar flow, Darcy's friction factor is inversely proportional to the Reynolds number, where Reynolds number is given by Vd rho by mu. Inertia force by, what is the definition of the Reynolds number? Inertia force by viscous force. So these are all the things to remember. See, some questions are damn sure. When you look at the flow through pipes in this discussion, how the velocity changes, how the shear stress changes in the laminar flow. Supposing in the turbulent flow, if you just look at this in turbulent flow, velocity distribution is not parabolic, rather it is logarithmic. That question may ask. U is a function of R, but it is not parabolic in turbulent flow, because in turbulent flow continuous intermixing is there. That is why this velocity distribution logarithmic velocity distribution in turbulent flow. In laminar flow it is a parabolic. In laminar flow parabolic, in turbulent flow it is logarithmic, where the Reynolds number is greater than 4000. Okay, you shall solve some questions which were given in the previous papers. I'll just try to quickly answer some of the questions there. Look at this. Unit of surface tension, answer is B. I already mentioned that. Relation between poise and one poise. One poise is 1/10 of Pascal second. That is 1/10 of Newton second per meter square. You can answer that. 1 poise is 1/10 of Pascal. Second, 1 Pascal is 1 Newton per meter square. You can easily answer this question. And a rectangular block is a good question there. A rectangular block, so having some area, rectangular block, area A of specific gravity x, block specific gravity rectangular block, and it is immersed, and height y. This is height y. Rectangular block height is y. The depth of immersion, I can call this as z. I am calling this as depth of immersion is a z. So weight should be equal to the force of buoyancy. That is, what is force of buoyancy? Weight of liquid displaced according to the Archimedes. This is called Archimedes principle, right? What is the weight? mg. mg is equal to weight of block. What is the force of buoyancy? Weight of liquid displaced. How much weight of the liquid displaced? This much only. This is the liquid displaced. What is that? Area into z into water, no? Specific weight of the water. It is all water, this. What is the weight? M is equal to, M mass should be written as volume into density into G, right? A into Z into rho of water into G. Volume is how much? Volume of the block, area into Y into rho, okay. What is the rho of the block? Specific gravity is given. Specific gravity is x. X into specific gravity is x is equal to rho of the body divided by rho of water, right? X into rho of water I could write, okay, into G, area into Z into rho of water into G. You can cancel many things there. Rho of the water G, rho of the water G. The area could be cancelled. Then Z will be equal to the xy. Z is equal to xy. Answer is A. In a flow net, the net angle 90 degrees. C. Streamlines and Bernoulli's equation, law of conservation of energy. Continuity equation is the law of conservation of mass. Euler's equation, only two forces we consider. What are the two forces? Pressure and gravity. C is the answer. If you consider the viscous, you will get also, if you consider pressure, gravity and viscous also, you get the Navier-Stokes equation of motion. Euler's equation, we consider only two forces, pressure and gravity. In the Navier-Stokes equation, pressure, gravity and viscous. The variation of a cross section of the shear stress is linear. Shear stress is linear and answer is C. Laminar flow, just now mentioned that. Shear stress is linear and velocity is a parabolic. Maximum velocity is 2. Maximum velocity is, answer is D. Maximum velocity at the axis, right? This will be the exactly double the average velocity. Velocity is a varying at different radii different. All this been averaged, that is the average velocity. Average velocity, how do you calculate? Discharge divided by area of cross section. This is the average velocity. But this Vmax is exact, Vmax is at the center line. Center line, this is a Vmax, center line axis is double the average velocity. In laminar flow only. For the flow of water through the penstocks of Idukki power plant, the head loss due to friction can be calculated by using Darcy-Weisbach. Darcy-Weisbach equation you can write. Darcy-Weisbach equation we can write for any flow. Whereas the Huygens-Poiseuille equation only for laminar. Only for laminar. This is any flow. Laminar or turbulent, we can write the Darcy-Weisbach equation. Answer is B. Type of fluid flow when the observer remains stationary is called as Eulerian. Answer is A. If you move along with the particles, it is Lagrangian. Center of buoyancy of a submerged body always coincides with the centroid. Answer is C. Supposing if the block is floating like this, if this much, this is the water, where is the center of buoyancy lies? Center of buoyancy lies at the centroid of the volume of the liquid displaced here. Here the center of force of buoyancy acts. Force of buoyancy acts at the centroid of the volume of the liquid displaced by the body. Okay. Answer is C. In a capillary tube, weight of the liquid is supported by a vertical component of the surface tension. I already mentioned this is like this. This is a sigma surface tension. Its vertical component will be balancing the weight. If this is the weight, it is balanced by the upward force. What is the upward force? 2 pi r sigma into cos theta. 2 pi r sigma into cos theta. This is theta. This is the balancing force. Weight will be acting downwards, right? This is the balancing force. This is the 2 pi r sigma, 2 pi r into balancing force will be 2 pi r sigma. Weight will be, what is that weight? What is the weight there? Mass into volume, right? Mass, density into volume. Or specific weight into volume. The mg will be rho density into volume. Volume will be pi r square h, if this is a h. Pi r square h, that is a volume. Sigma into all, this gives the mass into g. So both should be equated. You may get the h. Pascal's law states that fluid is in a fluid at rest. Answer is B. The pressure at a point is same along all the directions. Px, Py at a point, Px, Py, Pz all are equal. The pressure at a point is same along all the directions. Fluid at rest. Velocity potential function when equated to a equipotential line. If the velocity potential is same for all the, what is velocity potential value? No, you got a velocity potential function x, y, z. If this value is same at all the points on a line, that is called as a equipotential line. Slope is also given. I have given the slope already. Slope of the equipotential line, remember that. dy by dx for a constant phi, also I had given, minus u by v. Due to variation of venturimeter, high velocities is not suitable. For high velocities, venturimeter is not suitable. X to the boundary layer thickness, you see, the boundary layer thickness for the laminar flow or a flat plate, it is x to the power of 4 by 5. For the laminar flow, this is the turbulent flow or a flat plate. For the laminar flow, the boundary layer thickness, this thickness is called boundary layer thickness, delta. This delta is in the laminar flow where the Reynolds number is less than 5 into 10 power 5. Here delta is directly proportional to the x to the power of half. In the turbulent flow, local Reynolds number is greater than 7 into 10 power 5. Delta is directly proportional to the x to the power of 4 by 5. This is the turbulent flow. This is transition. This is turbulent. Delta is the hydrodynamic boundary layer thickness. Delta is hydrodynamic boundary layer thickness. one poise is equal to 1/10 of Pascal second, 1/10th of Newton second per meter square. B cannot be the answer. 1 Newton is equal to 10 to the power of 5 dynes. Now you can check that dynes actually. 1 Newton is 10 power 5. And 9.81 Newtons is equal to 1 kg force. So B cannot be the answer. 9.81 Newton per Newton is 1/10, 1 Newton is 1 by 9.81 kg force, right? B cannot be the answer. 1 Pascal is 1 Newton per meter square. You can check all these units there. 1 kg force is 9.81 Newtons. So answer will be C should be. Answer should be the C. What is the kinematic viscosity is 6 Stokes. 6 Stoke. Okay. 6 Stoke is 1 centimeter square per second. Okay. 6 centimeter square per second. 6 into 10 power minus 4 meter square per second. Dynamic viscosity is equal to rho into kinematic viscosity. Rho is given as specific gravity 2. 2 into 1000. Specific gravity is equal to density of the fluid divided by density of the water. Density of the water is how much? 1000 kg per meter cube. 2000 into what is the kinematic viscosity? Got 6 into 10 power minus 4. It should become Pascal second or Newton second per meter square. But 1/10 of the Pascal second is poise, right? 1/10, this is a Pascal second. So we have to mention in the 1/10 of the Pascal second is 1 poise is equal to 1/10 of Pascal second. Pascal second means as given, Pascal second is given, you have to divide with 10. You have to divide with 10, you will get one of the answers there. Answer is 12 poise. This is the thing. 1 poise is 1/10 of Pascal second. Printer sink is example of thixotropic. Printer's thixotropic is this. This is the shear stress. This is the Bingham plastic. This is thixotropic. This is thixotropic. The Newton's law of viscosity physics. This is Bingham plastic. Bingham plastic example is toothpaste. This is toothpaste. This is the thixotropic. Answer is C. So with this, actually I have covered almost all the topics very briefly, but try to follow that my notes and try to revise some of the important concepts. Wish you all the best. Good luck in the afternoon. I will cover the thermodynamics. Okay. Hello, hello. Hello students, welcome back. This is Sekhar from Msigma Gokulam. This is a thermodynamics comprehensive work I would like to do. Thermodynamics comprehensive work point of view, I am going to cover the subject. Okay. Thermodynamics is basically dealing with two different forms of energies, heat energy and work energy. Thermodynamics is basically a core branch of mechanical engineering that is dealing with two different forms of energies, heat energy and work energy, which are mutually convertible into each other. Okay. So, thermo is the word pertaining with heat, dynamics is the word pertaining with work. So, what is this macroscopic and microscopic point of view of thermodynamics? See, and as in the microscopic point of view of thermodynamic analysis, we will have to go into the details of the molecules, individual molecules, how they are moving, how their average motion is occurring. All the details we have to individually look at the molecular level. That is called as a microscopic analysis. But we never do that. That will be done in the statistical thermodynamics, which is beyond your scope of the subject. So, what is our analysis is a macroscopic on a bulk basis. For example, a room is there. A room may be containing so many crores or millions of molecules of air. Okay, but we don't go into the details of the molecular behavior. Okay, rather we will analyze the system. Rather we will analyze the system on a macroscopic basis, on a bulk basis, on the whole basis. Like we will be measuring the by using a thermometer, we will be measuring the temperature. By using the manometer, we will be recording the pressure, like that. So, on a macroscopic property basis, we will be analyzing the thermodynamic system rather. Okay. So, thermodynamics, if we just look at it, it is dealing with the two forms which are mutually convertible into each other. In the macroscopic analysis, of thermodynamic problem, we always try to measure the average properties of system, like pressure, temperature, volume, etc. Okay. But in microscopic analysis, particularly in statistical thermodynamics, we will go into the details of individual molecular behavior. Which we never do in our analysis. This is not the thing what we do. Okay, but we always do in macroscopic analysis of the thermodynamic problem, individual molecular behavior, and then take statistical average behavior. Of system, right? So, this is all about the macroscopic and macroscopic behavior and all difference there. Now, what is the main important thing what we have to notice? Thermodynamic system. It is a fixed region in space upon which our attention is concentrated for thermodynamic study. System and surroundings are separated by the system boundary. This is the system boundary. Boundary separates the system and surroundings. Okay. The boundary can be expandable. Boundary can change its shape. Need not that boundary is fixed in shape. Boundary can change its shape also. Okay. So, thermodynamic system broadly classified into three categories. This is how the questions are asked: closed, open, and isolated. closed system, open system and isolated system. In the closed system, no mass transfer between the system and the surroundings. No mass transfer between system and surroundings. But energy transfer could happen. Heat may enter, heat may leave, work may enter, work may leave. But Q and W transfer possible. Heat and work transfer possible. They are the energies in transition between the system and the surroundings. Heat and work, in thermodynamic point of view, heat and work are the energies in exchange. System may be supplied with some energy, heat. Our system may be rejecting so and so heat. We will be doing some work on the system, or we are getting some work from the system. See, so there is always a energy and energy transfer occurring between the system and the surroundings via boundary. That is why heat and work are boundary phenomena. That is why heat and work are, they are the boundary phenomena. They are occurring via system boundary. Heat and work are energies in transition. They are not the properties. Mind that heat and work are not properties. They are the energies in transit, energies in exchange between the system and the surroundings via system boundary. So whenever you talk about the heat transfer, you look at the boundary and then try to understand how much energy interaction is happening, heat or work. So best example for the closed system is, best example I could give is a piston in a cylinder. A gas is there. This is a closed system. This is the best example for the closed system is gas in a piston cylinder. Okay. Then open system means both mass and energy transfer can occur between system and surroundings. Both mass and energy transfer can occur between system and surroundings. Best example is, so many examples, I would like to plot it. This is an open system. So for example, this is the mass may enter, mass may leave. Mass can enter, mass may leave. Mass transfer is there. Mass in, mass out. There may be a heat transfer, there may be work transfer. This is also can be called as a control volume. This is a best example for the open system. Heat may be rejected. Heat can be rejected also. Work may be done on the system. See, most of the thermodynamic systems are open only. Majority, most, I can give countless examples like turbine, fan, compressor, blower, diffuser, nozzle, pump, boiler. These are all the open systems actually. If you just look at the examples of the open system, nozzle, blower, turbine, compressor, pump, throttle valve, diffuser. Okay, you can give even many more actually. Boiler, turbine, compressor, fan. Fan is a open system. Okay. So sometimes work may be zero, sometimes heat transfer may be zero. If heat transfer is zero, such a device is called as an adiabatic. Adiabatic means no heat transfer. Okay. So these are all the open systems. Like this can also be called as control volume. Another name of the open system can be called as a control volume. The boundary of the control volume can also be called as a control surface. Okay. And come to the isolated system, third one, isolated system. In the open system, we have the mass transfer and work transfer. Heat may be supplied, heat may be rejected. Okay, this is a supply, this may be rejected, this work may be done on the system or by the system. For example, if you look at the turbine, work done is positive, work done by the system. Here the work done is negative, we have to do the work. Pump also, work done is negative. Diffuser fan also, work done is negative. Why negative? Because we have to do the work, otherwise fan cannot, because we are supplying the electric power to the motor in the fan, motor is driving the fan. Compressor also same way, pump also same way, but only positive work we get from the turbine, a gas turbine or a steam turbine. Okay. And isolated system means neither mass transfer nor energy transfer. Neither mass transfer nor energy transfer can occur between system and surroundings, right? Neither mass transfer nor energy transfer can occur between the system and the surroundings. Best example for the isolated is example. I am giving the two examples for the isolated system. I will give the two examples. Number one, thermos flask. Number two, thermodynamic universe. What do you mean by thermodynamic universe? We have defined the system. We have defined the surroundings. Everything external to the system is called surrounding. Between the system and surrounding, there is a boundary. System plus surroundings put together is called system plus surroundings put together is called thermodynamic universe. Thermos flask, there is no heat transfer between the system and the surroundings, right? Thermodynamic universe means system plus surroundings. So these are all the examples for the open system. Those two are the examples for the isolated system. Okay, we have defined the system. Now I will define the how to analyze how to describe the system. How to describe the system? To describe the system, we require some tools. We have a system. Say, for example, a room or a compressed cylinder, a cylinder containing compressed air. We want to describe it. On what ways you can describe? By defining the properties. So properties are the tools. Properties are the tools meant for describing. Sorry. Properties are the tools meant for describing the state of a system. So thermodynamic properties. So these are tools. Properties are the tools meant for describing system, meant for describing thermodynamic system. What are the tools means? Actually, example, pressure, volume, temperature, internal energy, enthalpy, entropy. These are all the properties. Okay. But to describe the state of a system, to describe the condition of a system, do you have to give all the properties? Need not be. Usually it is sufficient to give the two properties. Just to mention sufficient to mention the two properties. Okay. From those two properties, other properties can be calculated. So most commonly we require to give any two properties. Usually we give pressure volume and temperature entropy. Pressure volume or temperature entropy. Any two of them will be sufficient for a simple compressible substance like gas in a piston cylinder arrangement. So these are all the tools. See, internal energy, this is internal energy, this is enthalpy, that is entropy, this is entropy, right? So these are by using any two properties we can describe the property of a system. We can describe the state of a system. This is the state, thermodynamic state. This is the thermodynamic state. The condition or configuration of a system, which is used to the condition or a configuration of a system, the condition or configuration of a system either mentioned by any two independent thermodynamic properties is called as a thermodynamic state. Okay. And properties can be broadly divided into two categories. Properties are broadly divided into two categories, intensive and extensive. Intensive properties, these are the questions they will be asked, intensive properties and extensive properties. What do you mean by intensive properties? Intensive properties are those which don't depend on the mass of the system. They don't depend on mass of system. Example, best example is pressure and temperature. They depend on the mass of system. Depend on example, internal energy, enthalpy, entropy, total entropy, volume is also main thing. They are all the total internal energy, total enthalpy, total entropy, total volume. All are total properties. All are total. Its units are kilojoules, kilojoule per Kelvin, S for entropy, like total entropy, V for total volume. But here one important thing here. Any specific property like this, see this is a specific volume. It is an intensive. Specific volume per kg. Whenever you say per kg in the units, it means that it is a specific property. Any specific property which is defined per unit mass is intensive. Any specific property which is defined for unit mass like specific volume, specific enthalpy, specific entropy, all are intensive. All are intensive. How do you know it is a specific? Per kg will be there. Total volume divided by meter cube per kg. Generally small letters will be used, no? U. All are intensive. These are all intensive, but total properties are extensive, mind that. Pressure and temperature, they are always intensive. Any specific property which is defined are intensive, total properties are extensive. Total volume extensive, total enthalpy extensive, specific volume intensive, specific enthalpy intensive, like that. Okay, now thermodynamic properties are the tools meant for defining the state. So this is the thermodynamic state. Whenever a system undergoes a change of state, like this, it is said to have undergone a thermodynamic process. Thermodynamic process is that change of state. System is undergoing a change of state. So this is called as the thermodynamic path. You got the intermediate state points. When you join all these intermediate state points, we get is a thermodynamic path. What is a thermodynamic path? Between the initial state and final state, there are so many intermediate states are there. When you join all the intermediate states, we are liable to get the thermodynamic path. Here, so this is a this is the thermodynamic state. This is a thermodynamic state. At a given thermodynamic state, we have only one property. One property. You take any property at that state. You take any properties, totally 6 are defined, U, P, V, UHS, PVT, UHS. So at a given thermodynamic state of a system, there is only one unique value for any property. You don't see the two pressures there. You will have only one pressure, you have only one volume, you have got only one entropy, one enthalpy, one temperature. So all these properties are called as point functions. When the point changes, when the state changes, the property value will change. I don't say that all will change, but some of the properties may be liable to change. So at a given thermodynamic state, there is only one property, there is only one unique value for any property. There is only one unique value for any thermodynamic property. That is why here come important note I am writing. That is why hence all thermodynamic properties are point functions or point functions. All thermodynamic properties are called as a point functions, or one more thing, exact. These are the questions that will ask. All thermodynamic properties are point functions or exact differentials. All thermodynamic, remember these statements. These are the questions they ask in the usually such exams. All thermodynamic properties are point functions or exact differentials or state variables. You can also say or state variables. Okay. Whereas heat and but heat and work, they are not properties, but heat and work are not properties, that is they are path functions, they are not point functions. They are, that is they are path functions or inexact differentials, or inexact differentials. So exact differentials are all properties are exact differentials. Heat and work are inexact differentials or path functions. Please remember that. They are path functions or inexact differentials. That is why delta Q and delta W are inexact. Whereas du, dp, dt, dh all are exact differentials. Whereas delta Q and delta W are inexact differentials. If these are the questions, property, they may ask definitely one question about the properties. What is intensive, what is extensive, what is exact differential, whether heat and work are properties. No, heat and work are not properties, they are the path functions. System never has a heat, system never has a work. Supposing a gas is there in a piston cylinder arrangement, do you say that system has got so and so heat? Wrong. We can say system has got so and so pressure, so and so volume, so and so temperature, because pressure, volume, temperature, they are all the properties. They are possessed by the system. Heat and work, they are never possessed by the system, they are always in exchange, in transition via boundary between the system and the surroundings. Between the system and surroundings, heat and work are energies in exchange, energies in transition. That is why they are called as a path functions. Okay, fine. So we understood about what is the difference between point function and path function. Okay, now at thermodynamic process I already said, whenever a system undergoes a change of state, it is said to have undergone a thermodynamic process. Usually the processes are usually drawn on PV or TS. Why generally these are very important is, any area, this area under PV curve will indicate work transfer. Similarly, area under any TS curve, area under any TS curve will indicate heat transfer. Generally process will, this path will always have some arrow direction indicating the direction of the process. Okay. So the area under this TS diagram, this may give, this is something talking about heat transfer. This is something talk about work transfer. Remember that. Okay. Right. Now what is the quasi-static process? Thermodynamic equilibrium. You should understand before that thermodynamic equilibrium. Thermodynamic equilibrium comprises three kinds of different equilibriums: thermal equilibrium, mechanical equilibrium, and chemical equilibrium. What is meant by thermal equilibrium? Here in the thermal equilibrium, the temperature difference between any two locations within the system must be zero. At every location within the system, if you see the same temperature, then the system is supposed to be in thermal equilibrium. Similarly, between any two locations within the system, if there is, don't see any pressure difference. Suppose the room is there, one pressure there, one pressure here. then it is not an mechanical equilibrium. We have to wait until if the pressure difference is there, automatically flow happens, and until both the pressures become equal. Then I say yes, it is in mechanical equilibrium. No chemical reaction. No chemical reaction. Even if reaction is there, the rate of forward reaction should be equal to the rate of backward reaction. So only when all the three equilibriums are satisfied, the system is supposed to be in thermodynamic equilibrium. Okay. Only for those thermodynamic equilibriums we can assign the property. The system can be assigned a property. We can plot it on a thermodynamic plane, either PV or a TS. Any plane, either you can select PV or TS. Mostly we select these two, PV or TS. Of course, two more are there, but we don't discuss in this particular subject. Okay. Okay. Then what is a quasi-static process? Process means, what do you mean by thermodynamic process? Whenever a system undergoes a change of state from one state to the another state, it is said to have undergone, it is said to have executed a thermodynamic process. Okay. A system is undergoing from some initial state to the final state. I say yes, system has undergone a certain thermodynamic process. When do you call this as a quasi-static process? This is the meaning of the quasi-static process. While undergoing a process, if each and every state, while system is undergoing a thermodynamic process, if each and every state undergone by the system is almost in thermodynamic equilibrium, though the deviation is happening, definitely the system is deviating from thermodynamic equilibrium, but the deviation is very, very, very small. Quasi-static means it occurs very, very slowly. While undergoing a process, while undergoing a thermodynamic process, if the deviation of system from thermodynamic equilibrium is infinitesimally small, if the deviation of the system from thermodynamic equilibrium is infinitesimally small, while undergoing a thermodynamic process, if the deviation of system from thermodynamic equilibrium is infinitesimally small, such process is called as quasi-static. Is called as quasi-static. Quasi means what? Semi. Quasi means semi. Static means system is undergoing. So it is like this. Supposing if the system is expanding from this position to this position in 1 year time. Just imagine, we can't do that. A system gas is expanding very, very slowly from here to here. If this expansion takes place in a time of say 1 year, yes, that can be thought of as a quasi-static. That means practical processes cannot happen like that, because all practical processes happen with certain speed. Okay. So in quasi-static process, the main thing is the deviation of the system from thermodynamic equilibrium is infinitesimally small. Though system deviates from the equilibrium, as it goes from one state to another state, it is deviating. No doubt it is deviating, but the deviation is very, 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 very small. Such process is called as a quasi-static process. Most important question answered here is work done by, please remember, such questions will be asked, work done by closed system during a quasi-static process. During a quasi-static process is given by integral PdV between the limits 1 to 2. Supposing if the system is undergoing a quasi-static process, this area indicates work done. This area is nothing but the integral PdV, that is the work done. Of course, to write this formula, two conditions must be satisfied. What are the two conditions? System must be closed and the process must be quasi-static. When these two are satisfied, yes, you can write the work done is equal to integral PdV, which is the area. The area under the PV curve is the, such questions will be asked. These are the questions that will most likely to be asked in this such kind of an examination. Okay. Now, when you talk about the equilibrium, thermal equilibrium, immediately we get in mind zeroth law of thermodynamics, because totally there are 4 laws of thermodynamics: zeroth law, first law, second law, and third law. Third law is not of much importance, but just learn the statement. Zeroth law, first law, second law are very important. Zeroth law of thermodynamics. From zeroth law of thermodynamics only we can define the property called temperature. Each law will be defining one property. From the zeroth law we can define the temperature, from the first law we can define the internal energy, from the second law we can define the entropy. So, the 3 main properties: temperature from the zeroth law, internal energy from the first law, entropy from the second law. Okay, these are the outcomes. Zeroth law, what does this law states? When 2 thermodynamic systems, namely A and B, are independently in thermal equilibrium with a third system C. What do you mean by thermal equilibrium? Equality of temperature. If 2 systems are in thermal equilibrium, their temperature are supposed to be same. When 2 thermodynamic systems A and B are independently in thermal equilibrium with a third system C, I am writing the statement. When 2 thermodynamic systems are independently in thermal equilibrium, with a third system C, then those two systems are in thermal equilibrium with each other. All 3 systems would have the same temperature. All 3 systems will have same temperature. So, temperature is the property defined from zeroth law. Temperature is the thermodynamic property defined from the zeroth law. Okay. Then comes the very important thing called as the first law of thermodynamics, which is also called as law of conservation of energy. Before going to the first law, I will define what is the cyclic process first. First I define what is a thermodynamic cycle. What do you mean by thermodynamic cycle? A thermodynamic system beginning at one state point, beginning at one thermodynamic state, it is undergoing maybe 2 processes, 3 processes or 4 processes. But after executing a number of processes, if the system comes back to its initial state where it has begun the journey, it is said to be called as undergoing a thermodynamic cycle. So, after undergoing a number of processes, here I am showing only two processes, but most of the thermodynamic cycles will have 4 processes. Most of them, Otto cycle, diesel cycle, etc., including Carnot cycle. They will all of them would have the 4 processes. But here I am just showing for the simplicity only 2 processes. 1 to 1 is thermodynamic cycle. Sometimes cycle may be clockwise, sometimes may be an anti-clockwise. If it is a clockwise cycle, that means heat engine cycle. All clockwise cycles are heat engine cycles, all anti-clockwise cycles are refrigerator or heat pump cycles. This is a work producing cycle. Okay. thermodynamic cycle. 1 to 1 is a thermodynamic cycle. And whenever a thermodynamic cycle undergone, what is the net change in the property of the system? 0. So, for example, because cyclic integral of dP or cyclic integral of dt or cyclic integral of dH, all of them should be equal to 0. Why? System has begun the journey here. At that state, there is only one pressure, one enthalpy, one temperature, one volume. So, because after undergoing the cycle, because system is reaching to the same state point where it has begun the journey, the net change in the property must be 0. But cyclic integral of delta W may not be 0. Cyclic integral of delta Q may not be 0. There may be a net heat transfer or a net work transfer with the cycle, but they are not the properties. Del W and delta heat and work are not the properties. Okay, along for any cycle, for any thermodynamic cycle. What do you mean by thermodynamic cycle? Beginning at one state, after undergoing 3 or 4 or 5 processes, if the system is reaching to the same initial state, it is said to have undergone a thermodynamic cycle. It is a clockwise cycle. All clockwise cycles are, this is a all clockwise cycles are heat engine cycles. All clockwise cycles are heat engine cycle. Anti-clockwise cycles are refrigeration cycle. Refrigeration or heat pump. Okay. Fine. Now we have understood what a thermodynamic cycle means. Net change in the property of a system during a thermodynamic cycle is 0, because system is coming to the same initial. At that state, there is only one pressure. So after undergoing a number of processes, it is coming to the same state. That means what is the net change in the pressure? 0, because it has reached the same state. At one state, there is only one property value. Right. Now I am stating the first law for a first law of thermodynamics for a cyclic process. It is a law of conservation of energy. Whenever a system undergoes a cyclic process, the net algebraic sum of all the heat transfers is directly proportional to the net algebraic sum of all work transfers. What do you mean by algebraic sum? Heat transfer has got a convention, sign convention. Q is positive if supplied to system. Q is positive if supplied to system. Q is negative if rejected from system. W is positive if work done by system. Expansion work, any expansion work is a positive. W is negative if work done on the system. Compression work. For example, fan is there. If you take the fan as a system, work is negative or positive? Negative. Turbine, work is positive, because from the turbine we get the work. in the compressor, in the fan, in the pump, we need to do the work. Therefore, work is negative. So, any expansion like for example turbine. In the turbine, work done is a positive, is negative, like a compression work or a pump work. Compression work like a compressor, fan, blower, these are all the negative works. So remember this. The equation says that first law of thermodynamics, cyclic integral of delta Q is equal to cyclic integral of delta W. This is called as the first law for a cycle. See, this round indicates cycle. It is valid for a clockwise cycle or a anti-clockwise cycle. Clockwise or anti-clockwise. Okay. And reversible or irreversible, anything you can say. Now actually you would like to say what do you mean by a reversible process. First of all, you should reversible is the word very important in the thermodynamics. First let me talk about the what do you mean by reversible process. See, suppose that a system has undergone a thermodynamic process. When do you call this as a reversible? When can you say this process is a reversible? Yes, this can be said as reversible if after undergoing a process welcome back students. Actually this is a thermodynamic process undergone by the system. When I can call it as a reversible? I can call this process as reversible if after undergoing the process, if the system can be brought back along the same path but in the reverse direction without producing any changes either in the system or in the surroundings. After undergoing a process, system must be able to proceed to the same initial state along the same path without producing any changes either in the system or in the surroundings. Such process is called as a reversible process. It can never happen practically. All the practical processes are to some extent or more, they are all irreversible. Okay. I am writing this. After undergoing a process, if the system can be brought back, to its initial state, along the same path, but in the reverse direction, without producing any changes either in the system without producing any changes either in the system or in the surroundings, either in the system or in the surroundings, such process is called reversible. Such process is called reversible. And there are many factors. There are many factors which will make a process irreversible. Some of the factors which will make a process irreversible are why a process becomes irreversible means there are so many reasons, or main thing is mechanical friction, rubbing friction, viscosity of the fluid, electric resistance. These are all some of the things that will make a process irreversible. Mixing of fluids is irreversible. Mixing of fluids at different pressures or different temperatures is irreversible. Heat transfer through a finite temperature difference. When heat is transferring through a finite temperature difference, it is irreversible. So because of so many things, there are many more are there. So because of all these things, a process finally will render to be irreversible. In every process, some of them or all of them are there. So all the practical natural processes are irreversible. Remember, reversible process is only an imagination. So but that quasi-static process is also called as irreversible. Quasi-static process is also called as reversible. Okay. Now, this first law of thermodynamics which we have defined earlier, first law of thermodynamics which we have defined for the cycle, no? This is valid for any cycle which is valid for any cycle, reversible, or valid for first law, valid for any cycle, whether reversible or irreversible or clockwise or anti-clockwise, anything it is valid. This is the first law for a cyclic process. Now I will give the first law of thermodynamics for a non-cyclic process, which is more important in the exam point of view. First law for non-cyclic process undergone by closed system. Non-cyclic undergone by closed. First let me discuss with the closed or a non-flow process. This is also called non-flow energy equation. There are two things are there, NFEE and SFEE. SFEE for the open system and NFEE for the closed system. Look at this. Suppose that a system is there, such kind of questions will come. You are supplying some gas is there, we are supplying some say 100 kilojoules of heat. Because you are supplying heat, is a positive or a negative? When you are supplying, it is positive. When you supply some heat to the gas or system, maybe some work has been done. This is Q122. Maybe around 70 kilojoules of gas might have expanded, right? It is also a positive. Okay. Then 100 you are given, 70 given out. What had happened to the remaining 30? The remaining 30 might have been stored by the gas, which is used to increase its internal energy. That is, first law of thermodynamics is law of conservation of energy. Like Bernoulli's theorem, that was also law of conservation of energy in FM. Similarly, here first law of thermodynamics also is a law of conservation of energy. Energy can neither be created nor destroyed. So you are giving 100, 70 got the work, remaining 30 the system has followed. System has taken off, system has absorbed, and that has increased its already existing internal energy. Already internal energy is there before supplying the heat, but that 30 kilojoules is swallowed by this system, which will be used to rise its internal energy. That is, this is the first law format for a non-cyclic process. It is delta U in change of internal, increase in internal energy. U2 is always final. Here in this case, if you write this plus 100 minus of plus 70, it will be plus 30. Right side always final internal energy minus initial. Internal energy has increased by 30 kilojoules. So this is the first law for a non-cyclic process undergone by closed system. This is also called non-flow energy equation. In differential form, it can be written like this: delta Q minus delta W is equal to du. That is in the finite form, this is in the differential form. And here the sign convention must be carefully taken. Supposing sometimes, I will give one example here. Some system is undergoing some process, some compression work. So 100 kilojoules, okay, and during that the heat transfer may be around 120 kilojoules. What is delta U? Supposing if he has asked what is delta U, we have to give the sign for every energy transfer, because we have already sign convention is known. Work done on, because the compression, no? This is compression means work done on the system, that means negative. Here clearly heat has been rejected, that is also negative. Heat rejected means negative. Now you can write the first law of thermodynamics. Original form is this U2 minus U1, but this minus is not the minus of sign convention of W, it is the minus in the equation. Now I will cleverly supply the values there. Q is minus 120 minus of, because this is minus in the equation, minus of minus 100. Why this minus written? Because work done on the system. Any compression means volume is decreasing. When volume is decreasing, it is a compression work, should be equal to the U2 minus U1. So plus 100, that becomes U2 minus U1 is equal to minus 20. That is the internal energy decreases by 20 kilojoules. So this is how we have to solve such kind of first law problems then. Okay. In this is also valid for any thermodynamic process undergone by closed system. Any thermodynamic, valid for any thermodynamic process, irreversible or irreversible, what do you think? Undergone by closed. But if the process is reversible, what is the other name of reversible process? Quasi-static, right? But if process is reversible, delta W is equal to PdV. What is the other name of reversible? Reversible or quasi-static. Both mean the same. Other name of reversible is quasi-static. Then delta Q is equal to du plus PdV. This holds good only for the reversible. This holds good for only for the reversible process. Only for reversible. Don't use it for the irreversible. This is valid for any thermodynamic process, general. Whereas this is valid only for the reversible, because delta W is equal to PdV is exclusively reserved for the reversible or quasi-static. Okay. Now this particular This particular equation I will apply to the constant volume, constant temperature, constant pressure for various thermodynamic processes I will apply. First law of thermodynamics for various thermodynamic processes undergone by closed system. Totally in thermodynamics we come across 5 processes: constant volume, constant pressure, constant temperature, adiabatic and polytropic. Usually 5 processes we come across. Constant volume means rigid container, heat may be supplied. Okay, volume rigid vessel, no? This is a rigid vessel. Mass is constant. No work done here. Here no work done because no expansion. The dV volume is G constant, dV is 0. When dV is 0, because V is constant, implies work done is equal to integral P dV. dV is 0 means work done is 0. Okay. Heat transfer is, heat supplied is mCV delta T. Here comes ideal gas. Actually working fluid, here I am making the one ideal gas rule, ideal gas concept. Ideal, what is that ideal gas? Which obeys PV is equal to, ideal gas obeys all the gas laws. Ideal gas says PV is equal to mRT. This is an ideal gas equation. So if you write the Charles law for the ideal gas, what is the Charles law of ideal gas says? If you think that if it is an ideal gas, air is an ideal gas. If you think example of ideal gas is air. Example is air. Air is an ideal gas which obeys this PV is equal to mRT. Obeys, ideal gas obeys PV is equal to mRT at all pressures and temperatures. What is the Charles law of ideal gas states? Volume constant means pressure is directly proportional to the absolute temperature. That is P2 by P1 is equal to T2 by T1, but both should be in Kelvin only. This is called Charles law of ideal gas. It is a constant volume process. Charles law says that for ideal gas like air, if the volume is constant, pressure is directly proportional to the absolute temperature. What do you mean by absolute temperature? Degrees Celsius plus 273, what we get is in Kelvin, right? Right. Now, work done is 0, and if you write the first law, Q minus W is equal to delta U, work done is 0, implies Q is equal to delta I. That is, in constant volume or isochoric. What is the other name of constant volume? Isochoric. In that means heat supplied is equal to increase in internal energy. Heat supplied is equal to increase in internal energy of system. Then comes constant pressure. Constant pressure or isobaric process. When you are supplying the heat at constant pressure, when you are supplying the heat at constant pressure, you have to allow the gas to expand. Unlike the earlier process, in the constant volume, you are allowing the pressure to increase, but you wanted to maintain the volume constant in the earlier one. Here, you are supplying the heat, but you want to maintain the pressure constant. How is it possible? You have to allow the gas to expand. So therefore, the Charles law here also is applicable. Working fluid is ideal gas, like air, ideal gas. Air is an ideal gas. Air is ideal gas. We can write the Charles law here also. Charles law states what? Charles law second statement. Charles law has got two statements. When volume is kept constant, pressure is directly proportional to the absolute temperature. Now the pressure is constant, pressure is remaining constant, volume of the gas is directly proportional to the absolute temperature of the gas. V2 by V1 is equal to T2 by T1, but both should be in Kelvin scale only. Okay. Now this area, because system is closed, this area can be thought of as work. This area can be thought of as integral P we already said. This is the work done. What is the work done? P into V2 minus V1. So many kilojoules. I already said integral work done is equal to integral PdV. Work done is equal to integral PdV. If the system is closed, it is a closed system, and if the process is reversible, I am assuming that process is also reversible. W is equal to integral PdV. We could write if the process is reversible and system is closed. So this is the work done, we got it, and heat transfer will be mCp T2 minus T1. Cp is the specific heat at constant volume. In this constant pressure process, very importantly, in this constant pressure process, heat supplied is equal to change in enthalpy. Remember, this is a change in enthalpy. What is this enthalpy? Like internal energy. So what is internal energy first of all? Internal energy is the sum of all the forms of energies of all the molecules contained in the system. Internal energy is a property. Internal energy is a property which is dependent only on the temperature for ideal gas. How do you understand internal energy? First of all, how would you understand internal energy? Any gaseous system may contain so many enormous number of molecules. Each molecule may be possessing some translatory kinetic energy, rotational energy, vibrational energy. If you sum up all these energies of all the molecules contained in the system, what you get is an internal energy, which is depends only on the temperature. Very important law. That law is also called as the Joule's law of ideal gas. For ideal gas like air, internal energy depends only on the temperature. Okay. And here another property called U plus PV. This PV, internal energy, plus what is that PV called? It is also called as flow energy. Internal energy plus flow energy is called as enthalpy. And for ideal gas, H is also a function of temperature only for ideal gas. For the real gas, H is dependent on both pressure and temperature. For real gas, which does not obey the real gas obeys van der Waals equation of state. Real gas obeys van der Waals equation of state, whereas ideal gas obeys ideal gas equation, PV is equal to MRT. Ideal gas obeys all the gas laws at all pressures and temperatures, and also it obeys PV is equal to MRT at all pressures and temperatures. And on the other hand, real gas obeys van der Waals equation of state. For real gas, internal energy and enthalpy are dependent on not only on temperature but also on pressure. Remember that point, that is a distinguishing thing. For ideal gas, internal energy and enthalpy both depend only on the temperature. That is called Joule's law. For real gas, which obeys van der Waals equation of state, for real gas which obeys van der Waals equation of state, U and enthalpy and internal energy depends are depend on not only on the temperature but also on the pressure. Okay. So, this is how we can understand that difference between ideal gas and real gas, and for particularly I want to say is heat transferred in any constant pressure process is equal to the change of enthalpy. Remember, whereas for the heat transferred in a constant volume process, earlier case, it is a change in increase of its internal energy. Heat transferred in a constant volume process is a change in internal energy. Heat transferred in a constant enthalpy process is a change of enthalpy. Then if you look at the isothermal or constant temperature process, and if your working fluid is ideal gas, if you think that most of the cases if the working fluid is assumed as ideal gas, what is the example for ideal gas? Air. In this case, the process will have a lesser slope. Slope of the curve is at constant temperature is minus P by V. This is the slope of the isothermal curve on PV plane. Here temperature of the gas is constant, that is T is constant, implies U is also a constant from Joule's law. From Joule's law of ideal gas. Working fluid is I am thinking as ideal gas. From Joule's law of ideal gas, U is a function of temperature only as such. So, U is constant means change in internal energy is 0. So, in the isothermal process there is no change in internal energy, no change in enthalpy also. Also delta is 0, no change in enthalpy. Why? Because for ideal gas enthalpy also depends only on the temperature. Here the Q is equal to W, because Q minus W is equal to delta U. When Q minus W is delta U, when delta U is 0, Q is equal to W. Work done is given by P1 V1 log V2 by V1. This is the formula for the work done in isothermal process, isothermal expansion. And isothermal process, heat and work transfer are equal in magnitude if the working fluid is ideal gas and no change in internal energy. Enthalpy also no change. Adiabatic. Adiabatic means what? No heat transfer. Adiabatic means no heat transfer between the system and surroundings. No heat transfer between system and surroundings. Q is 0. Gas can do work on the surroundings adiabatically without any heat transfer. Gas can do work adiabatically on the surroundings. At the cost, no adiabatic means no heat transfer between the system and surroundings. Equation of the process is slope is more here. Isothermal as compared to the isothermal curve, if this is the isothermal, this is adiabatic. If this is isothermal, this is adiabatic. Adiabatic curve has more slope as compared to the isothermal curve. Adiabatic, this is adiabatic, right? PV, this is PV to the power of gamma is equal to constant, where gamma is called as Cp by Cv. PV to the power of gamma is equal to constant. P1 V1 to the power of gamma is equal to P2 V to the power of gamma. Gamma is Cp by Cv. We know that gamma is a ratio of the specific heats. Gamma is also called as adiabatic index. Gamma is also known as adiabatic index of the gas. Usually it is 1.4 for air. Okay. Here the heat transfer is 0. Then work transfer is equal to P1 V1 minus P2 V2 by gamma minus 1. Gamma is Cp by Cv. Okay. And here if you write the first law, Q minus W is equal to delta U. Q is 0. That means W is equal to minus delta U. That is, work done by the gas is equal to the decrease in internal energy. Work done by gas adiabatically is decrease of its internal energy. Work and change in internal energy are equal in adiabatic. And lastly, we will have the polytropic process. Polytropic means, see, PV to the power of n is equal to constant. If you keep n is equal to 0, you will get the isobaric. If you keep n is equal to 1, you will get isothermal. This is isothermal, right? Isothermal process is PV is equal to constant. If you keep n is equal to gamma, you will get the adiabatic. If you keep n is equal to infinity, if n is equal to infinity, you will get a constant volume. This is isochoric. Now, if you keep the n value, if 1 less than n less than gamma, like PV to the power of 1.25 is equal to constant, it is called as polytropic. Because why it is called polytropic? N may take any values of any value between 1 and 1.4, maybe 1.1 or 1.2 or 1.3, like that. Here, work done during the polytropic will be P1 V1 minus P2 V2 by n minus 1. And heat transfer during the polytropic will be gamma minus n into gamma minus 1 by work done during the polytropic. Okay. These are the, so all the 5 processes you have to remember. For all the 5 processes, you have to remember what is heat transfer, what is work transfer, what is change in internal energy. And remember that in general, I can say, in general, for any thermodynamic process undergone by undergone by ideal gas, for any thermodynamic process undergone by ideal gas, delta U is equal to mCV delta T and delta H is equal to mCP delta T are valid. Any thermodynamic process irrespective, but only precaution is it should be ideal gas, or what is the other name of ideal gas? Perfect gas. Ideal gas or perfect gas both mean the same. It obeys all the gas laws at all pressures and temperatures. These two are valid for any thermodynamic process undergone by ideal gas. Internal energy changes are proportional to the temperature changes. Also the enthalpy changes are also proportional to the temperature changes. Right. All the 5 processes you have done. Now I will do the first law of thermodynamics for steady flow open system. First law of thermodynamics for steady flow open system, right? Now earlier first law, 2 modules of the first law I have taken. For a cyclic process we have discussed, for a non-cyclic process undergone by closed system. Now I am doing the first law for a steady flow open system. What do you mean by steady? This point I have discussed in the FM also. Steady flow means various flow characteristics like pressure, density, specific volume, temperature, whatever it is, at a particular point at the location must not change with respect to time. If various flow characteristics, various fluid properties, various thermodynamic properties at a particular point will not change with respect to time, it is called steady. They may be different at different locations. Here pressure may be different, here may be different. But that pressure here, whatever the pressure you see now or after 1 hour or after 2 hours, it remains the same. So for such flow, this we are discussing this open system. What do you mean by open system? Mass may enter, Mass may leave, mass can enter, mass may go out. This is called as the open system. And heat may enter, heat may leave also, and work may be done by the system, work may be done on the system, right? This is also called as, many times it is called control volume. The other name of the open system is called as a control volume. Control volume is surrounded by control surface. This mass which are going, this is the inlet, this is the inlet section is called 1, exit section is called 2. Okay. This mass while going into the control volume for steady flow, m dot 1 is equal to m dot 2. Mass flow rate at inlet, both the mass flow rates must be equal. This is the mass conservation of mass. Continuity equation also we can say. First law, if you say the format, law of conservation of energy, Q minus W is equal to delta H plus delta Ke plus delta P. What is this delta Ke and delta P? This mass while going, it will take 4 forms of energies along with it. The mass while going into the control volume, it can take 4 different forms of energies, that is internal energy, flow energy, kinetic energy and potential energy. So thus some of these two can be thought of as enthalpy. Similarly, this mass while going out can take away these 4 forms of energies: internal energy, flow energy, 2 for the exit section, this is exit, 2 for the exit, kinetic energy and potential energy. So again the sum of these two can be called as enthalpy, right? So this is a positive sign supplied, this is work done by the system. If you take work done by the system, that is also positive. So this is a heat transfer is positive, heat supplied and work done also by the system, that is also a positive. So then for unit mass you can write, for unit mass H2 always right side this is the generalized SFEE which you can write. This equation only is called as steady flow energy equation. This is only called as steady flow energy equation for first law of thermodynamics applied to steady flow open system. In this, 2 is exit, 1 is inlet. What is that Z? Z is the potential energy, elevation. Z is the elevation, V is the velocity. This V is the velocities, not the volumes. These are the velocities. Okay. These are the enthalpies there. And per unit mass, this is for the total mass I have written, this is for the unit mass. That is why joule per kg. Now this can be applied for so many thermodynamic processes undergone by the steady flow open system. For so many steady flow open systems, we could write this as such. Just take that 5 minutes break. After the break, I will continue. Can we get some tea? Hello students, welcome back to the class. Now this is the steady flow energy equation which I have derived for the steady flow open system. Now I would like to apply this steady flow energy equation to various open systems in the thermodynamics. First thing is nozzle. Now I write the applications of SFE. If you write the nozzle, for the nozzle Q is 0, adiabatic system, work done is 0. Nozzle is an adiabatic system. Okay, high pressure fluid will enter with the enthalpy H1 and in this direction enthalpy, pressure, temperature all decrease for the fluid. What is the purpose of the nozzle? To increase the velocity, but it enters with a very low velocity, leaves with a very high velocity. Enthalpy decrease, pressure decrease, temperature decrease, all will decrease, but what will increase? But velocity increases a lot, increases greatly velocity. So what do you get? How do you get the velocity at the exit? Square root of 2 into h1 minus h2 joule meters per second. So this is our exit velocity for leaving the nozzle. This is one important steady flow open system. No work transfer, no heat transfer, but only pressure drop. No work transfer, no heat transfer, pressure drops, temperature drops, enthalpy drops, all decrease, but only velocity increase greatly. Number 2, throttle valve. Throttle valve is another important thing. In throttle valve, as the fluid passes through a very narrow passage, very narrow restricted passage, when the fluid passes through a narrow restricted passage, its pressure decreases. Okay. When the fluid passes through a narrow restricted passage, throttling means passage of fluid through a narrow restricted passage, through a very narrow restricted passage. Q is 0, W is also 0, no change in no delta Ke is 0, no change in velocity, no change in potential energy. Therefore, delta H is 0. Enthalpy remains constant during throttling. In throttling process, so throttling is an isoenthalpic process. Therefore, throttling is an isoenthalpic process. Throttling is an isoenthalpic process. As the fluid passes through a narrow restricted passage, entropy increases. During throttling, entropy increases, but delta S is greater than 0, delta P is less than 0. Entropy increases, pressure decreases, but enthalpy constant. Enthalpy constant. Pressure decreases. Pressure decreases. Entropy increases. Okay. So thus throttling is an isoenthalpy process, constant enthalpy process. Now if you put it for the turbine, in turbine enthalpy drop, fluid may enter with enthalpy H1, fluid may leave with enthalpy H2. System is adiabatic. Mostly all the adiabatic turbines are adiabatic systems, where adiabatic means what? No heat transfer between the system and the surroundings. Therefore, work will be obtained. A lot of work will be obtained. Work is equal to H1 minus H2 in turbine. Same thing for the compressor. If you like the compressor there, what is a compressor? What is a compressor? Pressure will increase. Enthalpy will increase, pressure will increase. We have to supply the work input. In the turbine, you get the work output, whereas in the compressor, we get the work input. We have to do the work, C for compressor. Therefore, work input is equal to, enthalpy will increase here for the fluid, H2 minus H1 kilojoule per kg. So, for various steady flow open systems, we have written the SFEE, throttle bar. So, throttling is a very important process. Throttling is an irreversible adiabatic expansion. Throttling is an adiabatic, but irreversible adiabatic. Now, if you come to the second law of thermodynamics, it has got two different statements. See, first law of thermodynamics is a law of conservation of energy. Second law of thermodynamics is also known as law of degradation of energy. Law of degradation of energy. It fixes the direction of the processes. The main difference between first law and second law is, first law cannot fix the direction of the processes, natural processes. Say for example, heat transfer is there. Can heat transfer occur between low temperature to high temperature? Can heat flow from low temperature to high temperature? Never. First law cannot say yes or no to that question. If I ask first law, can heat transfer occur from low temperature to high temperature? First law says I do not know. But second law clearly says it is not possible. Heat always flows naturally from high temperature to the low temperature. So that it fixes the law of degradation, it fixes the direction of the natural processes. That is why it is called as law of degradation of energy. Second law says heat energy is a low grade energy. So according to second law, Q is low grade energy. And work is high grade energy. That is the that grading of energies is done by second law of thermodynamics. It has got two statements there. One is a Kelvin-Planck statement. Kelvin-Planck statement. Two different people, Kelvin-Planck statement. It is impossible, very important statement there. It is impossible to construct a heat engine. It is impossible to construct a heat engine. It is impossible to construct a heat engine operating in a cyclic process which will produce no effect other than the transfer of heat from a single thermal reservoir and do equal amount of work. It is impossible to construct a heat engine operating in a cyclic process which will produce no effect other than the transfer of heat from a single thermal reservoir and do equal amount of work. So this is the a heat engine, cyclic heat engine from a single thermal reservoir. It is a negative statement. It is not possible to construct such a heat engine. Single thermal reservoir. What do you mean by thermal reservoir? Which can supply any amount of heat or which can receive any amount of heat without change in temperature. This heat engine is extracting some heat, and all the heat it is completely converting into the work. No one can manufacture such a heat engine. It is impossible to construct a heat engine operating in a cyclic process which will produce no effect other than the transfer of heat from a single thermal reservoir and do equal amount of work. this is just not possible to manufacture such a heat engine. Then what kind of heat engine is possible? Only this kind of heat engine is possible. A heat engine, a cyclic heat engine, must operate between two thermal reservoirs. One is at high temperature and other is at low temperature. Any cycle, what is the first of all heat engine? What do you mean by first of all heat engine? A heat engine is a cyclic device. A heat engine is a cyclic device which will receive some heat and produce some mechanical work. A heat engine is a cyclic device which receives the heat from some source. This is a heat source. This is the source of heat. This is called as a sink, to where heat has been rejected. This work should be, W should be less than Q1, and the remaining thing, heat must be rejected. Heat rejection, this is heat supply. It can convert only a part of the heat supply into the work. Remaining heat, it has to reject it to the sink. Examples for the heat engine are 3 examples I can give: steam power plant, IC engine. Best example for the heat engine is internal combustion engine, or a diesel engine, or a petrol engine. You are burning some fuel there, you are generating some heat. Only a part of that heat generated we are converting into the work which is able to drive the vehicle. Remaining heat we are rejecting to the sink. Sink means atmosphere. For all the heat engines, the surrounding atmosphere is the sink. How are you rejecting heat in the IC engine? By the exhaust gases leaving the silencer, or by the radiation heat given through the fins, etc. We are rejecting some heat to the sink. Sink is an atmosphere, right? We cannot convert all the heat supply totally to the work. If it is converting, it is violating the second law of thermodynamics. If any machine that violates the second law of thermodynamics, it is called as a PMM2, perpetual motion machine of second kind. PMM2 violates second law. Okay, this is a heat supply, this is a heat rejection, this is a work. And here comes the thermal efficiency. Thermal efficiency of any cyclic heat engine is net work done per cycle divided by heat supplied. For any heat engine we could write, that is Q1 minus Q2 by Q1, or W by Q1, or 1 minus Q2 by Q1. This is the formula for thermal efficiency of any cyclic heat engine. Okay. Q2 is the heat rejection, Q1 is the heat supply, W by Q1. Q1 is the heat supply. Work is so heat engine is a cyclic device which receives some heat from the source and converts a part of that heat into the work. Right. Now, another statement is Clausius statement. It is another second statement. It is impossible. It is impossible to construct a device. It is impossible to construct a device operating in a cyclic process. Operating in a cyclic process, which will produce no effect other than the transfer of heat from a low temperature thermal reservoir to a high temperature thermal reservoir. Or it will never, heat will never flow. Heat will never flow from low temperature to the high temperature without the expense of external work or agency. Heat will never flow. Yeah, it has got another statement also, another way also it can be stated, or heat will never flow from low temperature to high temperature without the aid of external work or agency, without the aid of external work or agency. You have to supply some work to make the heat to flow like this. It is an impossible statement. One device is there, one device. We are transferring heat from low temperature to the high temperature. This is device, right? We are transferring some heat. This low temperature to high temperature. Nobody can manufacture such device. Only all the practical devices, they require some work to be supplied to make the heat to flow, from low temperature to the low temperature to the high temperature. To make the heat to flow from low temperature to high temperature, we have to supply some work. So in fact, this is a best example is refrigerator, heat pump, are both are the examples for the devices which receives the heat work from some external source and transfer the heat from low temperature to the high temperature. Okay. So according to the Clausius statement, it is not possible to make the heat to flow from low temperature to high temperature without supply. If you supply the work, you can make the heat to flow from low to high. Both the devices operate on this principle only, refrigerator and heat pump. Here it defines the important definition called coefficient of performance. Coefficient of performance, that is useful effect wanted by work input. See, for example, in case of the refrigerator, this is a high temperature, this is a low temperature. Useful effect wanted is Q absorbed from the low temperature reservoir is the useful effect wanted. In case of the refrigerator, useful effect wanted is how much heat we are extracting. For this device to operate anti-clockwise, you require some work. Your refrigerator cannot work without supplying the electric power. Can you drive the refrigerator? Not possible. So this is the input, this is the useful effect. So this useful effect divided by work input is the coefficient of performance, COP of the refrigerator. COP of the refrigerator is Q absorbed from low temperature divided by work input. Similarly, for the heat pump, here the Q rejected to the high temperature this is the useful effect. Q rejected to the, this is the COP of the heat pump will be Q rejected to the high temperature reservoir divided by work input. Okay, so according to the Clausius statement, COP of any either refrigerator or heat pump can never be equal to the infinite. It is not possible. Okay. Right. Now, both Kelvin-Planck statement and Clausius statement. Clausius statement and Kelvin-Planck statement are the two different statements of the second law, but both are equivalent. That means violation of one statement automatically lead to the violation of the other. Both Kelvin-Planck statement and Clausius statement are equivalent. That is, violation of one statement automatically lead to the violation of the other. Violation of one statement automatically lead to the violation of other. Now, in this case, now I would like to introduce the most important heat engine, which has got the highest thermal efficiency. Therefore, according to Kelvin-Planck statement, you may see here, according to Kelvin-Planck statement, no heat engine can have a thermal efficiency equal to 100%. Supposing if this is 0, it will be 1, right? That means without rejecting any heat, you are converting all the heat supplied into the work. That is not possible according to the Kelvin-Planck. So, according to the Kelvin-Planck statement, no heat engine can have 100% thermal efficiency. No heat engine can have 100% thermal efficiency. And no refrigerator can have infinite COP. Supposing COP there, in the COP formula, if work done is 0, that means without supplying any work, you are transferring heat from low temperature to high temperature. When W is 0, what is the COP? Infinity. That means according to the Clausius statement, no refrigerator and no heat pump can have infinite coefficient of performance. So that also you can understand. So any device is like that, it is called PMM2, perpetual motion machine of second kind. But there is one engine having the highest thermal efficiency, but not one. That engine is called as a Carnot heat engine. If you just look at the Carnot heat engine cycle, which is operating having a 2 isothermals and 2 adiabatics, 2 reversible adiabatics. It is also called as a reversible heat engine. Carnot heat engine, it is also known as the reversible heat engine cycle. So there is a heat supply, there is a heat rejection, right? This is operating between the two temperatures T1 and T2. So Carnot heat engine, what is the specialty is, it is the engine having the highest thermal efficiency among all the heat engines. No heat engine can have a thermal efficiency more than that of Carnot. Okay. So the thermal efficiency of Carnot heat engine It is only dependent upon temperatures between which the heat engine is operating, 1 minus T2 by T1. T2 is the sink temperature, T1 is the source temperature, and both the temperatures must have to be in Kelvin. No heat engine can have a thermal efficiency. No heat engine can have thermal efficiency greater than that of Carnot. No heat engine can have thermal efficiency greater than that. And thermal efficiency of Carnot heat engine is independent of nature of working fluid. No, in fact, working fluid thermal efficiency, working fluid cannot have any dependency on the working fluid cannot have any influence on the thermal efficiency of the Carnot heat engine or reversible heat engine. Any the thermal efficiency of the Carnot heat engine is that specialty is that whatever the working fluid you use, the thermal efficiency of the Carnot heat engine will be the same as long as the temperatures between which the engine is operating is same. As long as the temperatures are same, its thermal efficiency will be the same for any working fluid you use inside it. Okay. So that is a very important thing. But Carnot engine cannot be made practically. Carnot engine is also called as a reversible heat engine. Okay. Now here I define a very important property called entropy. Entropy S. S is entropy is an outcome of second law, just like internal energy is an outcome of first law and temperature is an outcome of zeroth law. Entropy is an outcome of second law of thermodynamics. How do you define entropy? Entropy is an extensive thermodynamic property of system which increases whenever heat is supplied to the system, and which decreases whenever heat is rejected from the system, and which decreases whenever heat rejected from system. Or it is a measure of molecular disorderliness. I can also say entropy is a measure of molecular disorderliness prevailing in the gaseous system. S is a measure of molecular disorderliness prevailing in the system. This is a measure of molecular disorderliness prevailing in the system. The change of entropy during an infinitesimally small change of state. The change of entropy ds is the differentially small change of state, differentially small change of entropy Suppose that a system is undergoing a differentially small change of state, ds is equal to delta q r by T. Units of entropy are kilojoule per kg Kelvin, specific entropy. What is the delta QR? Delta QR is the differentially small amount of heat supplied reversibly at a temperature T Kelvin, where delta QR is the differential amount of heat supplied to system reversibly at a temperature T Kelvin. Differential amount of heat supplied to system reversibly at a temperature T Kelvin is the delta. You can show it graphically also, mathematically also, like this. Temperature versus if you take a differentially small amount of change of entropy, this is ds at temperature T Kelvin. Okay. So, delta Q is equal to TDS. This is valid for only reversible process. Valid only for reversible process. And if you integrate this, Q1 to 2 is integral TDS. This is the area of TS curve on x-axis. Just like, see, this is a very important point. In the work regarding the work, I already said, area of any PV curve on x-axis indicates the work done during the quasi-static process, work done during the reversible process undergone by closed system. I already said that. In case of regarding the work, area of the PV curve on x-axis will indicate the reversible work done or quasi-static work done by closed system. Okay. Here similarly area of TS curve on x-axis indicates area of TS curve on x-axis indicates heat transfer during the process. So this area is the heat transfer. Okay. So that is very important. That is why Carnot cycle on TS plane also we can plot it like this. The Carnot cycle on TS plane indicates this is T1 Kelvin, this is T2 Kelvin, this is a heat supply, this is a heat rejection. So, thermal efficiency of the Carnot heat engine or reversible heat engine is 1 minus Q2 by Q1 is equal to 1 minus T2 by T1. So, if you just look at that, or T1 minus T2 by T1, if the gap between the two temperatures keep on increasing, the thermal efficiency also increases. As the gap between them decreases, thermal efficiency decreases. And similarly, the reversed Carnot cycle also you can mark. The reversed Carnot cycle is used for the Carnot refrigerator and the Carnot heat pump. This is the clockwise cycle, original Carnot heat engine. The same cycle is reversed, it is a reversed Carnot cycle. It is the reversed Carnot cycle which may be used for the Carnot refrigerator or the Carnot heat pump. Here this is the Q rejected, this is the Q absorbed. reversed Carnot cycle, which you can use it for the Carnot refrigerator or Carnot heat pump. COP of the Carnot refrigerator is equal to TL by low temperature divided by high temperature minus low temperature. Remember this formula, very important. This is the original Carnot heat engine cycle, Carnot heat engine cycle, this is. Whereas this is the Carnot refrigerator, reversed Carnot cycle, this is a reversed. This is a reversed Carnot cycle which may be used for the Carnot refrigerator or the Carnot heat pump. This is for the heat engine cycle. What is a heat engine? It gives the work output, it takes the heat from some source and converts a part of that heat into the work. Then what is the reversed Carnot cycle? It absorbs the heat from the low temperature and transfers it to the high temperature, which can be used by either by Carnot refrigerator and Carnot heat pump. Refrigerator and the heat pump both do the same thing, both do exactly the same thing. But why there are two names? Based upon the what effect you wanted. If the Q absorbed is the useful effect wanted, that is called refrigerator. If the Q rejected is the useful effect wanted from the device, useful effect wanted from the device is the Q rejected, that device is called as a heat pump. So both do the same thing, but the COP formulas are different based upon the useful effect. Then similarly Carnot heat pump COP will be COP of the Carnot heat pump TH by TH minus TL. COP of the Carnot heat pump will be TH by TL. So you can also say that COP of the Carnot refrigerator plus 1 is equal to COP of the Carnot heat pump. Now the changes of entropy during various thermodynamic processes. During various thermodynamic processes. Constant volume process, if you take, volume process, this is you are supplying the heat, ds delta S, change of entropy during the constant volume process will be mCV log T final by T initial. This is the for the change of entropy during a constant volume process. Similarly, constant pressure process, if you take, change of entropy during a constant pressure process will be mCp log T final by T initial. Both must be in Kelvin. This is a constant volume, this is for a constant pressure process, isobaric process. Here also both the temperatures must be in Kelvin only. And constant temperature process, if you take isothermal or constant temperature process, see, look at this. This is the constant temperature process. If you write the first law, delta Q minus delta W is equal to du. If the working fluid is ideal gas, temperature is constant means internal energy is also constant. Already that point I have mentioned. For ideal gas, internal energy depends only on the temperature. Okay. So du is 0 because u is constant. Delta Q is equal to delta W. Heat supplied is equal to work done if the isothermal process are constant temperature. But if the process is reversible, generally almost all the many thermodynamic processes are assumed as reversible. Delta Q is equal to TdS and delta W is equal to PdV if the process is reversible. If you substitute that one there, TdS is equal to PdV, ds is equal to P by T dV. It is PV is equal to RV. PV is ideal gas. You know what is ideal gas equation? PV is equal to RT. That is an ideal gas. So if you integrate, you will get S2 minus S1 is R log V2 by V1, or you can also write Cp minus Cv is R log P1 by P2. Any formula we can use. This is the change of entropy during an isothermal or constant temperature process. Okay. Then comes the most important process is adiabatic. Adiabatic means no heat transfer. In thermodynamics, adiabatic means Q is 0. That is the meaning of adiabatic. But delta TdS ds is equal to delta Q by T. We are telling delta Q is 0 by T. That is ds is 0, S is constant. That means entropy remains constant during adiabatic process. Entropy remains constant during adiabatic process provided there is a condition supply, provided it is a reversible, because ds is written for the delta QR only for the reversible adiabatic process, provided I am writing provided the adiabatic process is reversible or frictionless. That means only reversible adiabatic process can be called as isoentropic process. That is, only reversible adiabatic process can be called as isoentropic process. S is constant. Isoentropic means S is constant. In case if there is a irreversibility, in case if there is irreversibility during adiabatic process, then entropy of this system will increase. Why? Why entropy of the system will increase? Because of the internal friction. So, that is entropy of an adiabatic process either remains constant if the process is reversible, or it will increase, it will never decrease. That means the entropy during an adiabatic, the entropy change during an adiabatic process where heat transfer is 0 can never be negative. I can say entropy of a system during an adiabatic process can never decrease. Either it will increase if the process is irreversible, or remains constant if the process is reversible or frictionless. That is, delta S during any adiabatic process, is greater than or equal to 0. Either it constant if the process is reversible. If it is greater than 0 means irreversible during any adiabatic process. Okay. That means the entropy, there are many things that you have to know, we have to understand about entropy. The entropy of a system can increase either two different ways it can increase. Either by external heat transfer, supposing there is a system. Principle of increase of entropy, if you think of principle of increase of entropy. Supposing if this is a system, this is the surroundings. The entropy of the system may increase either by heat supply or by internal irreversibilities. Even this is 0, still the entropy of the system can increase. The entropy of system can increase either by external heat interaction number 2 or by internal irreversibilities like friction Either ways, both are there means it will increase. Suppose if this is not there, external heat, still it can increase by internal irreversibilities. Okay, and supposing and we can say the change in entropy of the thermodynamic universe is always greater than or equal to 0. What is thermodynamic universe? Delta S of the system plus delta S of the surroundings put together. It is always greater than or equal to 0. The entropy of the thermodynamic universe will never decrease. We can also say the entropy of thermodynamic universe will never decrease. Either it will increase or remains constant. Thermodynamic universe means system and surroundings. Suppose that it is like this. There is a system. There is some heat interaction. Then as a result of this heat interaction, delta S of the system is positive and delta S of the surroundings is negative. Why delta S of the surroundings is negative? Because surroundings are losing. Delta S of the surroundings is negative. The one is positive, one is negative. But but if the process is reversible, delta S of the system plus delta S of the surroundings will be 0. This algebraic sum, it will be 0. It will positive negative. And if the process is irreversible, and if the same process is irreversible, then delta S of the system plus delta S of the surroundings will be greater than 0. That is, entropy of this entropy change of the universe will never be negative. Either it will increase or remains constant. When it will remain constant, if the process is reversible. When it will be irreversible, when the process is irreversible, the net change in entropy of the system plus surroundings will be greater than 0. This is called as principle of increase of entropy. Any irreversible process like heat transfer from high temperature to the low temperature, or mixing of fluids, or anything, any kind of irreversibility prevailing during the process will finally result in the increase of entropy of the universe. Entropy of the universe will never decrease, and total energy of the universe is constant. That is called first law of thermodynamics. Entropy of the universe will never decrease. Available energy. This available energy concept, availability and irreversibility, the available energy concept must be understood based upon the what is the lowest possible sink temperature. See, if you look at the Carnot heat engine, we know that Carnot heat engine thermal efficiency is dependent upon 1 minus T2 by T1. Okay. For a given heat supply, as T2 got reduced, T1 is fixed. As T2 got reduced, efficiency will increase. Efficiency will, as the T2 got reduced, as this got reduced, as this got reduced, this ratio will decrease and efficiency will increase. But how long this sink temperature we can reduce? How much low? Means the lowest possible sink temperature is that of the environment, that is T0. As T2 decreases, thermal efficiency of Carnot heat engine increases. That means more work. You get the more work, right? When the efficiency is increasing for a given heat supply, you get more work. But the lowest possible sink temperature is that of environment. T0. We can't expect that sink temperature to be lesser than that of environment, because all the heat rejections are happening to the environment. How can you change the atmospheric temperature or environment temperature? Can you change? Never. The surrounding environment temperature, atmospheric temperature, we cannot change. So for any heat engine, the lowest possible sink temperature is that of the environment. That is why environment plays a significant role. Available energy is, supposing for a given heat, for a given amount of heat supplied, what is the maximum useful work you can expect when operating between the temperature of T1 source and the environment temperature should be T0, rejecting heat to the environment. The available energy is the how much maximum work obtainable from a given heat supply to a heat engine. Available energy is the maximum amount of work that may be obtainable for a given heat supply. Therefore, available energy is the maximum work obtainable from a given heat supply to a cyclic heat engine. Available energy with environment as the sink. With environment as sink. Okay. That means available energy, I can write that available energy will be the thermal efficiency into Qs, that is 1 minus T0 by T1 into Qs. That is the available energy. And unavailable energy is the minimum amount of heat that is to be rejected to the sink. Okay. So, in the concept of available energy or the availability under the irreversibility, the atmosphere or the sink plays, atmosphere or environment as the sink, it will play a significant role. See, as you keep on decreasing the T2, no doubt efficiency will increase, but how long you can decrease? T0 lowest temperature is that of the environment. T0 is, whenever you given a suffix at environment temperature, that is T0 Kelvin. T0 is a symbol for environment. So, 1 minus T0 by T1, this is the available energy, and this available energy is indicated by this particular area, we can say. The area of the rectangle will also give the available energy. And then what is availability? Availability of a process. What is this availability concept? Supposing a system is there, it has got certain pressure, certain temperature. It is executing some thermodynamic process. How long that process could happen? The system can go on expand. How long it can go on expand? Until the pressure and the temperature of the system will reach that of the environment. Suppose that system is executing one thermodynamic process. How long it can expand? Can it expand indefinitely? No. Once the pressure inside the system reaches that of the environment pressure, and once the temperature of the system reaches the environment temperature, there is no more work you may expect from the system. That means the system has reached a dead state. This is called as a dead state. Dead state means system has arrived at the same pressure and same temperature as that of the environment. You can't anymore expand, you can't expect any more work. Not possible. Once the system pressure has become equal to the environment temperature, once the system temperature has become equal to the environment temperature, I say that system has reached a dead state because you cannot expect any more work. So, availability concept says that availability of a system, is defined as maximum useful work. Maximum useful work that is obtainable from a system, maximum useful work that is obtainable from a system is defined as maximum useful work obtainable from a system before the system comes to thermodynamic equilibrium with its surroundings. Before the system comes to thermodynamic equilibrium with its surroundings. There is an availability function also, availability function. U plus P naught V minus T naught S. This is the availability function. So, maximum useful work would be equal to the maximum useful work would be equal to the decrease in availability function, decrease in availability function of system. Availability function is it a composite function? It contains the environment temperature. These two are that of the environment. Decrease in availability function will give the maximum useful work. And lastly, irreversibility I. Irreversibility I or the last work. It is the product of ambient temperature and delta S of the thermodynamic universe. This is the irreversibility or last work. T naught is the environment temperature in Kelvin. Environment temperature in Kelvin. Delta S is the increase in entropy of the thermodynamic universe. T naught is the environment temperature. This is the last work. That work is forever last. We can't get. Irreversibility or the last work is given by the product of the environment temperature and the change in entropy of the thermodynamic universe. Now I shall solve some previous papers questions which were given in the previous years, that in this comprehensive coursework there are some previous questions are there. Which of the following is an extensive property? Volume. Density. See, density is the reciprocal of specific volume. Specific volume is also intensive. Specific volume is also intensive. Therefore, density is also intensive. Answer is A. Pressure, all the three are intensive. An ideal gas at 27 degrees Celsius, all temperatures we have to convert into the Kelvin, is heated at constant pressure till volume becomes 3 times. V2 by V1 is 3. What is the temperature of the gas? Final temperature is asking. Pressure remaining constant, V2 by V1 is equal to T2 by T1. This is called Charles' law, from Charles' law of ideal gas. Charles' law of ideal gas. T2 is equal to T1 into volume becomes 3 times. T1 into 3. 300 into 3. 900 Kelvin. All temperatures in Kelvin. All temperatures in Kelvin. Okay. 900 Kelvin means minus 273. It becomes 627 degrees Celsius. Answer is D. For a simple closed system of constant composition, difference between the network and identifiable change in internal energy. Delta Q minus delta W is equal to du. Or Q minus W is equal to delta I. Answer is D. Flow energy means PV. Flow energy is PV. Answer is D. Flow work or flow energy means PV. A 4 kilowatt 20 liter water heater is switched on for mid. Heat capacity is given. There is a water and there is a 4 kilowatt, power is 4 kilowatt, current is applied. Therefore, Q heat generated is equal to all the electrical energy. Heat generated is equal to all the heat generated is gone into heating the water. Power into time is equal to mCp delta T. Power is 4 kilowatts. How much time? 20 later. 4 kilowatts, 10 minutes. 10 into 60. 1 liter has 1 kg. 1 liter water has, this is 20 liter means 20 kg. 1 liter has 1 liter has 1 kg mass. Cp is 4 into delta T. You can calculate delta T easily. 4 into 10 into 60 by 20 into 4. 4 gets cancelled. 30. Answer is D. All the power, electric heating, that heat will be given to the water only. In throttling process, which of the following? Already said throttling is an isoenthalpic process. Throttling, temperature may increase or may decrease. In throttling, there is one important coefficient is there. It is called Joule-Thomson coefficient. In throttling, one important coefficient, you remember this also. Mu is equal to 0 for ideal gas. For ideal gas, mu is equal to 0. During throttling, during throttling of ideal gas, if it is an ideal gas, during throttling of only ideal gas, not for other substances, during throttling of ideal gas, temperature also remains constant, but not for other cases. But here ideal gas is not mentioned. Temperature of ideal gas during throttle, temperature also remains constant along with enthalpy. Enthalpy anyhow constant. Temperature also remains constant if it is an ideal gas. Throttling of an ideal gas only. For other substances, temperature changes. But in any throttling, enthalpy is constant. Any throttling, enthalpy is a constant. Delta Q by T is 0. That means adiabatic, right? It is adiabatic. This means adiabatic. But entropy is increasing. That means the process is irreversible. Irreversible adiabatic. I already said delta S during an adiabatic process is greater than or equal to 0. Equality sign for reversible, greater than sign for irreversible. Answer is B. In the adiabatic process, entropy will never decrease. Entropy never decreases during the adiabatic process. Adiabatic means no heat transfer. If engine operating on a Carnot cycle, 1/4 of the Carnot cycle, this is Qs minus Q rejected by Q supplied. For any heat engine, this is the rule. Okay. Work output is 1/4 of the work. This is the Q rejected. This is the Q supplied. Okay, this is the heat engine. This is 1/4 of the QR. Then what is Qs? QR plus W. Okay, sum of these two is this. So 1/4 of QR, one fourth of the heat transferred to the sink, heat rejected, that is. QR plus 1/4 of QR. Okay, 1 plus 1 by 4, 1.25 QR. Qs is a 1.25 QR. Therefore, thermal efficiency is Qs minus, Qs is 1.25 QR. 1.25 QR minus QR divided by 1.25 QR. This is 1 minus, QR gets cancelled, 1 minus 1 by 1.25. 1 minus 1 by 1.25. You will get one of those answers. (125 by 100), 100 by 125. 125 minus 100 by 125, that is 25 by 125, that is 1 by 5. 1 by 5, right? 1 by 5 is 0.2. Answer is C. Answer is C. Because for any heat engine, this should be the sum of, this is arrow entering, this is arrow leaving. According to the first law, this is first law of thermodynamics. This is first law. Okay. Qs should be equal to the Q rejected plus W. That is the first law of thermodynamics. Which of the devices Clausius statement? Clausius statement operates on only one. That is, answer is 4. D only. Because only this is, all others are heat engines. All three are heat engines. But he is asking about the Clausius statement, refrigerator, or one more chance also is there, heat pump. Refrigerator and heat pump only operate on the Clausius statement. For a given difference between T1 and T2 increases, COP of a Carnot heat pump. COP of Carnot heat pump high temperature, T1 by T1 minus T2. As this is increasing, COP decrease. As T2 decreases, Carnot COP decreases. Answer is B. Which of the following entropy of a pure crystalline substrate? It is the third law of thermodynamics. This is only called third law of thermodynamics. The entropy of a pure, this is correct. Reversible heat independent of this is also correct. All the heat engines given a temperature source, none has a higher efficiency than a reversible engine. That is also correct. All three are correct. D is the answer. The first statement is the third law of thermodynamics. This is called third law. Carnot theorem, no, nothing can have a more efficiency than Carnot, and reversible heat engine and Carnot heat engine same. Reversible heat engine means Carnot heat engine. Other name of the Carnot heat engine is reversible heat engine, not a thermal prime mover. A. It is not, all others are thermal prime movers. All contain heat. It has no heat business. Here, no heat business. Okay. Minus 40. C by 100 is equal to F minus 32 by 180. This is a conversion, right? Both will be equal at minus 40. Answer is D. C is equal to F. You will get minus 40. Latent heat is the latent heat means the heat that will be given change of state from liquid to the vapor. Liquid to the gaseous or vapor. Answer is D. Latent heat on a temperature entropy diagram. This is the latent heat. Heat required to convert, this is liquid, this is vapor. More correctly, you should give it the vapor state, but he has given the gaseous, but vapor and gas both mean the same almost. So this is called latent heat. Any heat that is used to increase the temperature is called sensible heat. Answer is D. Energy can neither be created nor destroyed. It's the first law of thermodynamics, law of conservation of energy. It's a heterogeneous system. Actually, there is no homogeneous and heterogeneous. Actually, if it is a mixture of ice, water and steam, see, that can be, actually it is a pure substance but a heterogeneous. Homogeneous means throughout the single phase, water, cooling fluid, water, single phase, gas, atmospheric air. D could be the answer, but actually the question itself there is a wrong. Maxwell thermodynamic relations. Maxwell thermodynamic relations are valid for all processes of thermodynamics because they are the property relations. In a throttling process, delta H is 0. A vessel having a actually volume has been given as 0.6 meter cube, that is not square, it is a meter cube. Specific volume is volume by mass. Volume by mass. Volume is 0.6, mass is 3 kg. This is the answer. .6 by 3. 0.6 by 3 will be 1.8, right? 0.2, sorry, it is 0.2 meter cube per kg. Gas contained in a cylinder is compressed. This is a gas is compressed. Compressed means work is negative. This is 5000 kilojoules. Heat interaction causes through the surroundings to be heated. It is a previous GATE question. This is given once in GATE 2004, I guess. It is a previous GATE question, directly as taken off. Heat rejected, minus 2000. Therefore, Q minus W is equal to delta U. Surroundings to be heated. This is the surroundings to be heated. When the surroundings will get heated, only they receive the heat. That means heat has been rejected, negative. Is delta. Why both are negative? This is the work done on the system. Compression, no? Compression means work done on the system. Minus 2000, that is 5000 minus 2. 3000 is the answer. Answer is C. See, take care of the sign. Why it is a work is negative? Work done on the system. All compression works are on the system, negative work. Expansion work is a positive. Entropy may be expressed as a function of pressure and temperature. Answer is A. So, with this, I have covered as quickly as possible the thermodynamics in the afternoon and morning fluid mechanics. Prepare in the similar lines, whatever the basics I had given, and definitely you will be able to answer most of these questions. Tomorrow you will have another subject. Okay. Wish you all the best. This is Sekhar from Msigma Gokulam. Any doubts you may have, I have the WhatsApp group, you may post any doubts there in the WhatsApp group, you may post. So wish you all the best, my dear students. Good luck.